sixth session of World Conference on Thermoelectrics and Materials. This session will be chaired by Dr. Chandana Rath Madam from IIT PHU and co-chaired by Dr. Rekha Verma from Triple IT Allahabad. The talks which we have in this session are by Dr. who is from Siri Pilani, Rajasthan, speaking on titanium nitride based EG fat pH sensor for chemical or biochemical sensing applications. And Dr. Govind Gupta from NPL will be speaking on the topic development of highly responsive optoelectric devices based on semiconductor heterostructures. So I welcome the chair and co-chair, Dr. Chandana ji and Dr. Rekha ji, to take over this session.
Good afternoon. Thank you, the organizer, for giving me this session to chair. And in this session, there are three talks, as he has already explained. The first talk is given by Dr. Rajkishore Das, and the co-chairman is Dr. Rekha Verma, Triple IT Allahabad. We have to check half an hour schedule because it is already delayed by 1 hour. So I welcome Dr. Rajkishore Das from University of Hyderabad to talk on this development of wearable thermoelectric generator for converting human body temperature to electrical energy.
एक माइक
So let's discuss about development of wearable thermoelectrics generator converting human body to temperature to electrical energy. So this is a new type of device, right, which is thermoelectric device based on nanomaterial thermoelectrics. Is it okay? I can stop it and hello.
पासवर्ड पूछ रहा है
वन चेंज करते हैं वन So what is thermoelectric generators? These are basically that some devices which can convert waste heat energy to electrical energy. Right? So based on this, if you have a flexible thermoelectric generators, and come to that will improve the Seebeck coefficients. Then at the nanostructure materials, the thermal conductivity, which is a key challenge to bismuth telluride particularly, because of that JT value is very less. So it is possible that simultaneously improving the Seebeck coefficient, improving the electrical conductivity and decreasing the thermal conductivity to improve the JT around 2 for commercial this technology, right? Which I will present here. How can you do this material challenge, right? By improving simultaneously electrical conductivity and Seebeck coefficients and decreasing the thermal conductivity, right? So this is the challenge for whatever to not commercialize the material for particular applications for energy harvesting devices. In this regard, our approach is very simple, right? So as you said that graphene oxide, reduced graphene oxide cannot be utilized, but these can be doped with the bismuth telluride or make a new nanocomposite where the graphene act as a improvement in the Seebeck coefficients and electrical conductivity. Same time, by some phenomena, photon blocking, you can reduce the thermal conductivity, right? So this is the approach we have done, and the bismuth telluride nano where we synthesize by calculate assisted methods. Then when you coat it with the graphenes in situ doped, the materials will be making some different kind of morphology. I will show you TM and FTCM images, right? So this is what is the approach to utilize the bismuth telluride, not the bulk material, but the unique one-dimensional nanomaterials, and same including a doped graphene which is high electrical conductivity. And some interference phenomena, the phonon blocking phenomena will be effective and reduce the thermal conductivity and simultaneously improve the electrical conductivity and Seebeck coefficients, right? So this is what the material is synthesized, and some characterization is done by like to confirm that actually nanocomposite formation and formation of bismuth telluride materials by XRD confirm it, right? So by talk with the graphene, the crystal structure did change of the bismuth telluride retained structures. Some functional groups attachment is there, which may be affecting the electrical conductivity that can be reduced by thermal annealing process, and that is what confirmed from that the material which is synthesized by the novel approach we are applying is actually the bismuth telluride nanostructures having the matching with the crystal structures, matching with the molecular bonding, right? So after confirming this material is synthesized properly, we do some Raman spectroscopy for the phonon part. Phonon interaction with the graphene and reduced graphene oxide with the bismuth telluride can be confirmed from the Raman spectra, right? So there is a shifting in the peak positions by dipping dope to the graphene, and that will have an interface between the graphene and the bismuth telluride nanostructure. So that is the key phenomena of reducing the phonon part, which is not hampering the electrical conductivity flow of electrons, right? So that is what we achieve by successfully doing a new synthesis methods and decreasing. This is the key results where the phonon part will be reduced, right? So different morphology has been obtained, right? So some nanowires when coated with the doped with the graphenes, that is not anymore a nanowires. Some are ended with nanotubes, graphene dope, bismuth telluride nanotube. Some are with the chain structure, and each and every morphology has direct effect on the JT value, right? So if you are taking pure nanowires, JT value is different because the electrical conductivity and thermal conductivity phenomena for this nanowire is different than a nanotubes which doped with the graphene. Similarly, the graphene doped chain structure has different phenomena occurring at the peak property. So by taking the same material with the different concentration, graphene with the same bismuth telluride, you can end up with different morphology, which is happening at the nanoscale. Is it clear? So if I'm taking X gram of bismuth telluride and doped with 5 milligrams, then 10 grams, 20 milligrams, same synthesis approach, maintaining the same synthesis parameter, but ended with a different morphology. And each morphology has a unique property in terms of electrical conductivity and thermal conductivity. At the same time, the spinning effect can be reduced and Seebeck coefficient can be increased. So this is the key area. That means what is the achievement? So utilizing graphene as a high electrical conductivity and high thermal conductivity materials, it is possible that the old bismuth telluride materials which is not showing the high JT value can be improved to 2. After 2, it can be commercialized. So you can be some smartwatch or laptop backside, this can be coated. These are very flexible. I'll show you how to fabricate this, very simple. You can do in your lab also, right? Not improving any costly instrument. And after confirming that 3 different morphology we obtained successfully by the synthesis approach we are applying, right? Now we utilize this to fabricate the thermoelectric devices, which is called thermoelectric generator by simple approach. So before that, we measured the thermal conductivity properties of this graphene doped bismuth telluride. Itself, bismuth telluride has very high thermal conductivity, but after doping with 10 mg of reduced graphene oxide, the thermal conductivity value is reduced to 0.248, which is the new one worldwide. So it is patented or published already by our group, right? So thermal conductivity is reduced from 0.38 to 0.2. Same time, the electrical conductivity increased 4-fold, which is by the novel approach by doped the reduced graphene oxide 10 mg with the bismuth telluride during the in situ synthesis, not like the 2 material you synthesize and make a nanocomposite. That will not work. We try, right? So during the synthesis of this bismuth telluride, you take the reduced graphene oxide and dope 10 mg reduced graphene oxide to open a unique morphology structure that will be having high JT value because of higher electrical conductivity, the presence of graphene, and due to the phonon blocking phenomena, thermal conductivity reduced to 0.248, right? So whatever the achievements we want to plan, it is successfully the result experiment, these are all our experimental result obtained is confirmed that we have high electrical conductivity and very low thermal conductivity by utilizing graphene as a dopant. Right. So next step to fabricate this device, very simple approach, don't need anything. You can buy the raw materials and utilize a Dr. blade which is 2000 or 1000 cost, and you can fabricate this device by simple techniques. So first, you buy all the precursor material for PDMS and do this simple skewering and mixing and desiccator and make a transparent flexible substrates which is PDMS, which can be utilized for your contact lens. So no problem to utilize in your body. It's compatible to our body because most of the contact lens you use in eyes are made with PDMS, right? So it is a biocompatible and human interface is okay, no issue for any side effects. Then you utilize this method, make a thermoelectrics, that material which is synthesis giving higher JT value. Take this material and you use a binders. Binder is required for a good adhesion between the PDMS and this material. Right? After adding the binders, then use the same ductor blade and coat it on the top of this PDMS substrates and hot pressing you do at some temperature, curing temperature 70 to 80 degrees centigrade. Finally, the device is made with N type. Similarly, you can make P type, make a junction, right? It can be repeated, so many blocks to improve the voltage. So in each one couple will give the voltage, but in this work right now, we have I will present only for one, only P type, N type bismuth telluride junction. That work is still going on, so I don't have a data right now, right? So after testing, really in a lab condition and human body, by putting in the arms, we are able to get 54.7 millivolt, right? That can be utilized for some application portable device, and we are trying to improve this to some 3 volt. 3 volt is required for pencil small battery, right? Which is utilized for most of the device. So 54 millivolt to 3 volt or 1 volt can be achieved by utilizing, instead of graphene has a lot of issue. We are planning right now for MGene. MGene is graphene like 2D materials, but it is made with titaniums. Titanium is a metal, right? Titanium or molybdenum, that's materials utilized to synthesize a materials graphene like 2D nanomaterials, showing maybe better property than graphene, but it is very good to mix with bismuth telluride because graphene is made with carbon, and that creates a lot of issue for interfacing and making the adhesion issue. That reduce your electrical conductivity part, right? So this is the next process going on to utilize engine doped bismuth telluride nanostructures. Utilizing the fabrication process, we are hoping that 4 times the voltage can be improved. 4 times means it can go to 200 to 500 millivolt. This is sufficient for small portable device to work on, and that is what the achievements. And instead of making a one junction or one couple, you can have 10 couples together, and each will contribute 54 millivolt. Then 10 will give you almost 1 volt to 2 volt, right? And you can have more also. So you can reduce the fabrication process by lithography and put, instead of putting that millimeter size, I can decrease this to lithography to make these lines micron level and put 10,000s, right? In 1 by 1 centimeter by 8 centimeter length, you can have a 1,000, 10,000 these devices. Each will contribute maybe this around this voltage. Then it can be go to even 50 volt also, right? Which is the current work going on in our group to achieve and utilize this for actually for phone operations. So whatever the smartphone you are utilizing, if you have that coating on the top screen, which is you are buying right now for not making scratch, that materials is made with PDMS. It's a transparent materials, and backside also can have a cover, right? That will give the energy to electrical energy to phone to be charged. So you don't need to be charged by any electrical. Right. So this is what my talk is, very brief, and 30 minutes, 20 minutes plan for 10 minutes per questions. So these are the what we achieved so far. So bismuth telluride and bismuth telluride new type of commodity material is first time developed in India, maybe worldwide, right? Second, we utilizing a simple, cost-effective, economical process to fabricated thermoelectric generators, which can be directly utilized in your human body part, or anywhere you can put this also. It can generate electricity, right? It can be improved more by utilizing a different kind of 2D nanomaterials, because as you know that reduced graphene oxide, pure graphene is very difficult to utilize interfacing with the material because of strong bond between carbon-carbon. And graphene oxide is a lot of disorder and defects, which create problem for the electrical conductivity, though it is helping for thermal conductivity part, right? So this is what from my side. Any questions you have, you are free to ask me. Yeah. Huh? FPSCM, yeah. Maybe FPSCM. This one? Yeah.
Which one is bismuth telluride and which one is this graphene oxide?
Bismuth telluride is not there, it is all doped. Bismuth telluride, I did forget actually. One simple nanowire is there. So first is 5 mg graphene oxide, second is 10 mg graphene oxide, third one is 5 mg reduced graphene oxide, and that one is 10 mg reduced graphene oxide. So all four are doped with graphene oxide and reduced graphene oxide.
Sir, in that high resolution transmission, that
Last one is TEM, HRTM. Yeah.
sir, are you establishing any like graphene oxide in that bismuth telluride?
Graphene, what is the HRTM is indicating that putting graphene oxide and reduced graphene oxide, which is creating a lot of disorderness. So if you see the disorderness in graphene oxide is very high as compared to reduced graphene oxide, and this is making some percent amorphous structure also, right? Which is not in the 10 mg RGO, though some dislocation and defect is there, but that's in compare the first one and last one, it is a little bit better microstructures, less disorder as compared to that, because we want to improve retain the electrical conductivity of reduced graphene oxide, which should not be hampered by this doping process due to bismuth telluride, right? So in that case, we do the HRTM, reduced graphene oxide 5 mg and 10 mg, the last two figures. The 10 mg is a same reduced graphene oxide doped with 10 mg and 5 mg, more different kind of microstructure you can obtain from more disorderness, right? Which is very clear expert to this, though some dislocation is not pure lines. So we are confirming that that can be improved further by thermoannealing little bit, reduce the defects, right? This is your questions?
But there is no interface of bismuth telluride and graphene. Like
Interface is here.
last where it is.
Interface will be present when you have two material nanocomposite, right? If you are making nanocomposite material, two materials uniformly dispersed, make secondary phase. But these are not like that. This is doped during in situ synthesis of bismuth telluride, right? So which is interface may be not present because of the doping process, and the percentage of concentration of RGO is very less as compared to bismuth telluride precursors. So we want that this should be typical. We want to study that bismuth telluride with the graphene oxide is going where, right? Still not clear to us, because better than 5 nanometer we don't have facility. 1 nanometer resolution is required to understand more depth, right? So that is not here. 5 nanometer, we have facility up to 5 nanometers. I think IIT Madras recently procured one which can go 1 nanometer. Only one facility so far. Huh? I don't company name, but it is one facility they are establishing, maybe established, called spherical aberration TEM. Okay. Doping is like, suppose I'm taking, no, let me explain you. Suppose I'm taking the bismuth telluride precursor materials X gram, and I want to dope, let's say, 0.1% of graphene oxide. Then I calculate for X gram source material. First I will synthesis pure bismuth telluride and find out what is the yield I am getting for nanostructured bismuth tellurides, right? Suppose X gram precursor material giving me 50% yield. That means actually X to 50% of X utilized for this bismuth telluride nanostructure, meaning is going in chemical synthesis process. Is not 100% yield, right? So now I calculate that what concentration I need doped, and that way I calculate that this is 5 mg, 10 Fg is more appropriate for some percentage. I don't want to higher doping levels, it gives more defects, right? So, and very less, then it's not showing any improvement. So this is the way what we did. Right? But there is no control. After the material is synthesis, you come to know actually what is your plant that may be not achieved due to a lot of contamination during cleaning process. Some other phenomena are going on at chemical synthesis, right? All right, so next, any question more?
We have time for one quick.
Yeah.
I'm with Commander Yogesh.
Huh?
I'm with Commander Yogesh, sir. I'm an Indian Air Force.
Yeah. We are making this for Air Force defense actually.
So it's a very good topic, sir. But I want to understand the practical utility in our life. Like for example, if I give you a practical example of application of this technology.
Suppose you are wearing a helmet or your fabrics with the jacket, right? Lot of inbuilt sensors. Suppose you are utilizing the flight operations that don't need power supply. In any conditions, if it don't from your body of temperature, it will operate all the sensors you have attached with you and some component in dashboard also.
Sir, my question is for two things. One is helmet mounted displays we have, and we do wear a helmet during flight, and at times pilot is flying for 5 to 6 hours.
Right.
So the heat is generated, and that heat can be converted.
Exactly. This is the word.
My point is, how much is the per square inch, or if I ask you for the voltage gradient which it can produce?
Temperature gradient is 1 degree, 2 degree difference. Suppose you put helmet inside, the body temperature, say in the they are maybe like 17 degrees centigrade or 15 degrees centigrade, and in helmet suppose 19 degrees centigrade is there, which is a surrounding, and your body is a hot, right? That much 2 degrees centigrade you can generate at least some voltage.
My question is the voltage it can produce in per square inch, like because helmet.
Oh, okay. So how much area it is required? Now it is depend upon the device, which is like right now 2 centimeter by 8 centimeters. Right. Right now we're making a band, this is wristband, that dimension, you can change that.
And then if we come to the wearable device, like you said, we have an overall which we, or the G suit which we wear.
Yeah.
So all those G suits, like if you calculate the surface area, it would be quite good for the voltage to be generated.
For your jacket, you can place so many in this device. Let's say 100. Each will produce, let's say 2 volt. 2 into 20, so 200 volts can be generated from jacket. The whole pride of the inside can be run, right?
So the next is what's the comfort level which you can achieve, because there will be some discomfort, man.
That we can discuss.
Right. Yeah. This part is not there, but thickness is micron. So nobody knows that you are wearing something. Right?
Any students?
Okay.
Okay, if there is no questions, let us thank Professor Das for a nice and practical. The next talk is by Dr. Ravindra Mukhia. He is from Seri Pilani. He will be talking on titanium nitride based EG-FET pH sensor for chemical or biochemical sensing application. So, Dr.
Respected chair, organizers, distinguished faculties and scientists, students, a very good afternoon to one and all present over here. So I will be talking about on titanium nitride based EG-FET pH sensor for chemical and biochemical sensors. So before I start my presentation, I would like to give a basics about the things on which I am going to discuss. Is about, as we know that the field effect transistor is a potentiometric device. So we'll start with the basic device and how they are being used for chemical or biochemical sensors. So that description I will explain you, and then we'll move to the materials, how they are being synthesized, how we have developed, and finally the application, how we can make it as a biosensor or chemical sensor. So that will be progressing. Yeah. Next. So the outline of, I will start with the basics of FET and ISFET, MOSFET, and then EGFET, process development, fabrication of those devices, characterization, and finally I will conclude. Next, please. So as we know that field effect transistor is a potentiometric device, and MOSFET, metal oxide semiconductor FET field effect transistor, is one device which we have been using since from the years, and most of us or almost everybody knows about it. So what is the difference between MOSFET and ISFET? That we are going to discuss in the introduction. And ISFET is an ion sensitive field effect transistor. Ions means any specific ion. It can be H plus ion. It can be any specific ion, just like arsenic ion or any other organic or chemical which is to be sensed. If you want to sense, either it can be directly sensed, just like H plus ion can be directly recognized with the ISFET. Similarly, arsenic can be detected, or some biomolecule or enzymes which want to detect can be detected with this kind of sensors using the fundamental physics of the MOSFET. That's why we call it as a ISFET, means ion sensitive field effect transistor, or EGFET. EGFET is an advanced version of ISFET which is easy to fabricate, easy to realize, cost effective, biocompatible as well as disposable, which is required for the biosensing applications. So that is the one. The application are domains are societal and strategic areas, water quality monitoring, and many others for like your blood sampling and blood analysis, diagnosis. There are the several applications are there. So what is going on presently in the market or in daily life or in the pathology, which we are using ion sensitive electrodes. That is basically made up of glass. That's why we call it as ISE, ion sensitive electrodes or ion sensitive glass. So that is not CMOS compatible. It is difficult to integrate with the electronics and difficult to process and process in biomaterials also. So that was the challenge which we want to overcome from that. They are miniaturized. So we want to have a glass free pH sensing applications based devices. That is ISFET and EGFET are under that category. They are miniaturized. Fast response, less than 10 seconds we can achieve whatever the sensitivity we want to achieve. CMOS compatible. Biocompatible is also another thing which we have developed, in particular this EGFET, which is titanium nitride. So it is CMOS compatible as well as biocompatible. Design flexibility and small volume analyte is required to have all the processing and detection of those analytes or ions, whatever is the species is required to be detected. Next, please. The figure, please go to the previous one. The one commercial such device is mentioned over here. You can see this one. So here the device which is mentioned over in the last, it will be dipped inside or immersed inside the analyte. It will be sensing this potential, and that will be processed, and finally display of the pH will be displayed on the detailed display. Next, please. So similarly, the device or systems which we are under process of developing, not only for the chemical but for biochemical sensing applications also. So let me start with the basic. Just both the device has FET, field effect transistor, which are potentiometric. So what is the difference between these two devices? You can see we have a source or drain which is reversible. Either way also you can use it. Here you have a source drain. Here we have metal gate. In case of ISFET, we have replaced the metal gate with the sensitive film, which is the dielectric film, or maybe sometimes can be conductive depending on the property of the material. But it has to be sensitive. So what are the issues and challenges which we have taken care of? The existing ISFET devices has low sensitivity. They have a drift because it has a sensing behavior and electrochemical effect as well as temperature effect, because it is basically a semiconducting device. So it has both the drift, electrochemical effects, temperature effects as well as semiconducting effects. Drift behavior will be different. Hysteresis will also be there. Non-linearity is a problem because it has to work from 2 to 14 or 1 to 14 has to be like that in such a manner that for most of the applications, so that it should be linear. What does it mean by? It means that it should have a same sensitivity from 2 to 7 and 7 to 14. In alkaline side as well as acid side, it should have a almost linear response. And modeling is also another challenge because most of the models developed so far are applicable for MOSFET or maybe for some micron MOSFETs, but there is no specific model available which takes care of electrochemical phenomena as well in the modeling. So that was also another thing. Next, please. So how does it work? So this is a simple schematic of the ISFET device. So when it is immersed inside the analyte, maybe like pH solution, buffer solution, standard buffer solution which we have, Then apart from this, we have source, drain, and this is the sensing film. In top of that, we have analyte, which is required to be detected or measured, and in between we have a reference electrode. So reference electrode has a function of applying the potential, fixed potential or varying potential depending on the modality how you want to analyze or sense it. This is the reference electrode made of AgCl. Ag means silver, AgCl means silver chloride, made up of AgCl silver electrode, by which we can apply the potential to this analyte and we can make the closed loop circuit, because circuit has to made in a closed loop manner. So similarly, this working principle you can see with this diagram also. We have a sensing field which is exposed inside the analyte, and this is a piezometric device. So potential has to be generated. So how it will be generated? That is explained in this figure. You can see this is the substrate structure. This is the sensing film. Here the ions interaction, inner Helmholtz IL, inner Helmholtz plane, outer Helmholtz planes. Depending on the size of molecule, the potential will be generated. Either H plus or OH minus will be accumulated on the inner Helmholtz plane or outer Helmholtz plane, and the potential will be generated, and which can be applied to this gate, just like we have on the MOSFET, and that's how the current source drain current will be flowing. Next, please. Now, how EG FET is different from the SFET? As I told you, it is biocompatible and as well as flexible. So how we will make it? We can use a flexible substrate also here. So maybe just like in previous speaker I said about PDMS. So here we have glass substrate. On top of that we have conducting layer. Just like ITO glass coated substrate or aluminum, some other materials can also be utilized. On top of that we have a sensing film which is titanium nitride in present case. So you can see when we have an external connected gate, this is a MOSFET, commercially available MOSFET, and the gate of this MOSFET has been extended. You can see by this G connection has been taken out, and this whole device has been connected with this extended gate. You are getting the point. Now the gate of a commercially available MOSFET has been extended and connected to this electrode. That's why we call it as an extended gate electrode, and we whole device operation is integrated with this MOSFET, function as a easy FET. Extended gate, this is extended gate, and this is FET, this is the FET. That's how we call it as a EG FET, and the rest of things, chemical reaction, electrochemical reaction will remain same. The same reference electrode, bias potential, and the working of the MOSFET, source drain current, how we measure it. Next, please. So if you go for the applications more in detail, it's pharmaceuticals, food, environmental, agriculture, biomedical, and petrochemical industries. So most places we are using pH sensors, but with a different resolution, different sensitivity, it is required. So in that respect, to make it as a more versatile, have a more linearity from 1 to 14 or 0 to 14, you can say, we have made it like this, and results I am going to discuss with you. What are the challenges? As I already have discussed, these are the challenges which are still live in case of EGFET also, but we try to overcome some of them. Next, please. The motivation was to develop FET-based pH sensor, which is glass-free, CMOS compatible, biocompatible, cost-effective spectrum techniques, which are available in commercially available industries like fabrication processes, and the final development of pH sensor, which is based on EGFET process or EGFET device, which is biocompatible as well as chemical compatible. Yes, please. Next, please. Here I will explain you more in detail about little bit physics. You can see we have an insulator, which is basically sensing film. Then the inner Helmholtz layer, which is the oxide electrolyte interface. The interface between the chemical and the material which is coated, which is sensing film, and the aqueous solution, which is the rest of the chemical, which is lying inside the beaker or bath somewhere, wherever you want to measure it. The same inner Helmholtz layer, outer Helmholtz layer, and their surface charge concentration or density, which is expressed by this equation, is considered for the analysis of the device. Next, please. Now, how does it progresses? Here we are giving an example of pH sensor. So how it gets calculated? Ultimately, we are going to measure the drain current because it is a MOSFET kind of structured device. So how does it happen? You can see in case of analyte, which is here in case of buffer solution, maybe from 2 to 12 or 2 to 14 we can consider. So what will happen, depending on the type of buffer pH solution, the hydrogen ion concentration will be changing. This will be as a basically pH. That's how we establish whether it is alkaline or it is acidic. So what will happen, the charges based on the H plus ions, the electrolyte insulator interface charge will be generated. Based on the charge generated, surface potential will be generated because these are all will be accumulated and transferred to the gate surface, and the threshold voltage will be varying. since threshold voltage is varying, drain current is going to change. That's how it is explained over here. You can see. We have a on x-axis we have a reference electrode, just like we have explained you what is the reference electrode. It is the electrode through which potential is being applied, and you can see for different pH solutions to getting a drain current of the same value, we need constant current, constant voltage philosophy. Why it is? Because we are applying a constant voltage, means VDS, drain to source voltage is fixed, and we are measuring constant current. So that's why making an extension of this particularly that pH buffer solution, it is 4, 7 and 10, and we are measuring this difference, and this difference is being divided by the number of pH, means 4 to 10 or 4 to 7, we take a difference of any two, divide by 4 to 7 minus 3, or between these two and divide 10 minus 7 is 3. So we'll have a delta V reference, which is called as a sensitivity, means around 50 millivolt per pH or 59 millivolt pH, like this we calculate. Next please. So now we go to the electrochemical model which we have developed for the analysis and making a more perfect. More perfect means closer to the theoretical limit, as I have explained you, inner Helmholtz layer, outer Helmholtz layer, and how the potential is being generated. This is source, drain and reference potential, and these are the difference potential, surface potential generated at the interface of the semiconductor device. Next please. Now I come to the simulation results. Based on the model explained before slides, we have developed the simulations or coding has been done, and we have generated the characteristic for 4, 7 and 10 pH solution. One is alkaline, one is acidic, and one is neutral 7. From this we have taken the transfer characteristic and output characteristic, and from these the sensitivity is found to be 59.3 millivolt pH. This is the case for titanium nitride based EG-FET. For same materials we have developed the EG-FET. Next please. Next please. The film titanium nitride which I am discussing, there are different ways by which this film can be achieved or can be realized or fabricated. So if you will see, there are different deposition techniques. One is PVD, physical vapor deposition. The physical vapor deposition can further be classified as sputtering, evaporation or pulse laser deposition. The sputtering can be DC sputtering, RF sputtering or pulse DC sputtering. In present case, we have used pulse DC sputtering because it does not require complex matching network, and it is easy and it can be realized more in easy way in a CMOS process line in comparison to RF, because it is costly. Once your matching network goes wrong, everything goes wrong. But it is not the case in case of pulse DC sputtering. I will explain how it works. The next one is chemical vapor deposition, LPCVD, PECVD, APCVD, atomic layer deposition techniques, thermal oxidation or electrochemical deposition, which is the chemical route of deposition. Next please. Here in sputtering techniques, the sensing film is the most critical element in case of this chemical or biochemical sensor. It is one of the most popular thin film deposition technique, which is based on physical vapor deposition. Here we are using magnetron assisted reactive sputtering, which is pulse DC. Pulse DC means it is not constant DC, it is DC with varying frequency. That's why we call it as a DC. Means sometimes we apply DC, then we put it off, then we apply DC, then we put it off. That's why we call it as a pulse DC. At how time frequency we are changing it, that is called the pulse DC. Next please. Now you see how it looks like. The equipment look like this. We are applying these pulses over here at this electrode, which is like a cathode, and where the target material, here in our present case the titanium material has been used, the plasma section being created over here, and the wafer is placed over here, so that by the reaction, reactive reaction means reactive gas, which is nitrogen in here in this case, and the organ which is reacted as a bombardment gas, sputtering gas. So here it is applied, and you see it is being deposited over here. Now why we call it as a pulse DC? You can see it is the DC voltage of minus 300 volt kind of, but we are making it off for some time. So that's why we call it as a pulse DC. Please next please. So what are the different parameters which affects the performance of this pulse DC reactively sputtered titanium nitride material? It is applicable for other materials also, but what are the critical materials are operating power, operating frequency, reverse type means negative pulse what we are applying to make it off, the operating pressure and flow rates of the gases, which is a sputtered gas or reactive gas. Substrate temperature also plays a critical role in this case. Next please. So now we'll look a few of them one by one. When we increase the power, the discharge voltage will increase, discharge current will increase, growth rate will increase, and gas flow needed will required will also increase. And these are some of the example parameters which we have created for titanium nitride. Next, please. When we increase the higher frequency, means pulse DC frequency, means frequency which is close in case from 10 kilohertz to 100 kilohertz, how it affects, you can see. We started from 25 kilohertz to 100 kilohertz. These are a few one, but we have executed a many more examples and experiments in that regard also. So what will happen in that case? The better stoichiometry has been achieved, you can see, with the increase of frequency. Insulator charging will decrease, ion current will increase, and target voltage required will be less. So this is the outcome of the experiments which we have performed with the pulse DC reactive splitting techniques. Next, please. So finally, for the deposition of titanium nitride, the optimized parameters were like that. 300 watt was the power, 10 minutes we deposited, 50 kilowatt was the frequency we used it, 10% average pulse of voltage means half negative pulse which we have applied, put it off, and these are the other gas flow parameters. Next, please. Now we did the characterization of those films like XRD, FSM, SEM. Then we see different peaks corresponding to the titanium nitride materials, whether it is 111 or 00, has been obtained with the help of XRD, and which was required for this also. EDX, this is the FSM image, and these are the content of the EDX. Please. Now come to the fabrication. Next, please. Here you will see for the ISFET fabrication, which is one version or older version of the FET-based device for the chemical biochemical sensors. We started with the P-type silicon 100. Then we did the oxidation, did the lithography, oxide removal. Then we went to the diffusion, source and drain diffusion. Then oxide and PSD means some phosphorus doped glass will be deposited, that will be removed, and the gate oxide also has been removed. Now we did the blanket deposition of oxide, which is the high quality, high density oxide, which will work as a gate oxide that is deposited. Then they did the lithography, source drain contact were open, metallization was performed, and then after the lithography, metal was deposited and was ended. Next, please. After that, what we did, in some cases, some materials don't have etchant, just like titanium nitride also don't have. So in that case, what we do the lift off process. So before that, we deposited photolithography like photoresist, and after that we deposit the material, and then by the lift off, we remove the photoresist, and then we get the desired material deposited on desired location. Finally, we did the lift off process, removal, and then we do the packaging of the sensor. Next, please. What are the different masks which have been utilized during these processes are like that. First level mask for the oxide removal. Gate oxide was before the gate oxide deposition. Gate oxide patterning, active area definition, contact formation means source and drain metal contact formation. And you can see the active region is here, but our source and drain is far away. Why it is? Because we need to take electrical contacts so that the chemical interaction should not affect the electrical contacts, which are conductive in nature and which are most of the time aluminum, which is not rugged or chemical inert in case of chemical and biochemical sensors. Next, please. Here you can see the some same images. These are the active area, reactive region, gate region. Next, please. Thickness of titanium oxide gate oxide deposition was around 500 angstrom in this case, and you can see this is the gate oxide. Next, please. This is the sputtering process. You can see how it looks like. This is argon plasma sputtering chamber when reactive process was going on. This is the loading and unloading chamber. Next, please. And this is the final device when it has come after the dicing. This is the gate region. This is source or drain, or maybe vice versa. This is contact for source and drain, and this is the SFET device. Next, please. This is the complete 4-inch wafer processing for multiple devices. So as sir was saying, we can have lithography techniques, and we can have multiple devices connected in series and parallel as you wish, and you can get more number of power. So similar one example, we have multiple devices fabricated over here. These are the MOSFETs fabricated for characterization, and these are the SFET devices. Next, please. On-chip fabricated MOSFET was there to characterize the IVCV characteristic of the device and predict the analysis of the device. This is the dicing. Next, please. These are the characteristic of titanium nitride SFET. You can see as we predicted in previous case. Here we could find around the simulation was around 53 point something. Now we are also getting 54 millivolt per pitch, close to what we targeted for. These are the fitting curves for 4, 7 and 10, and you can see how much is the difference, and we can normalize it and we can get the sensitivity. Next, please. This is the titanium nitride SFET characteristic for different VGS. This is basically output characteristic. for 0 to 3 volts, 0 to 3 volts for PH4, PH7 and PH10 for 0 to 3 volts. What will happen when you apply the different bias voltage, means output characteristic VDS, so what will happen, there will be change in the current. So that can be observed, and that will be different for different pH values. So if you want to measure for suppose 3 volt, so in case of all 3 volt for 4, 7 and 10 will be measured, and then you have to take the relation, and that's how you have made the fitting curve. Next please. Now these are the final physical physics dimension, and these are the model fitting curves. These are the dotted points of the model fitting curves, and the straight and the lines are the experimental works. So ultimate target was to make a super model so that it can model the electrochemical behavior as well as semiconductor behavior. So that we perform, and you can see this is quite well matching. Next please. Drift analysis, as I said you, it has a semiconductor parameter as well as electrochemical parameters. So in that case, what is the drift, how it is varying with the time, that also was analyzed, and these are the results which was measured. Next please. Now we move to the EG-FET fabrication. Next please. Why we have moved explicitly, it is summarized over here. It is cost effective, means it is costly, it's not costly, it is cheap, less temperature sensitive because it inherently doesn't carry any active semiconducting device inherently in it. SPET has an active semiconducting device, but EG-FET don't have active semiconductor amplifying device in it, inbuilt in it. Less temperature sensitive, light insensitive. Semiconductor MOSFET is a semiconducting device which is inherently a light sensitive, but EG-FET is not a light sensitive. Less sensitive, I should say more appropriately. Simple packaging, because we don't have a source and wanted coming from two terminals. We have extension of the terminal, so we can take it out easily. Disposable in nature because it is simple electrode, so which is 1 minute. Over, it's okay. Okay, I'm coming. Wire connections are parasitics, are not as much as in case of SPET. Wet and dry environments are very separate. Next, please. Okay, this is the device, sensing film, ITO substrate glass, and this is the glass substrate. We can use the flexible substrate like PDMS also. Next, please. This is the measurement of the devices. This is the circuit which I have explained earlier. Next, please. These are the characteristic. This is the transfer characteristic, and this is the sensitivity plot. Next, please. Here in these are the different reliability sensing also has been performed for a period of time. Next, please. Excuse me. These are the drift analysis for 4, 7 and 10, how it is look like. You can see it is better than the previous one. Next please. Now I almost at the closing slide. So titanium nitride film for SPET, ACFET, both the devices has been fabricated, characterized successfully, and it is observed that the EG-FET has a better response in comparison to SPET because it is a more effective area. It is less light sensitive, it is less temperature sensitive, and the integration as well as interconnection making is much more easier. And that's it. Next please. Yeah, this is the last part but not least. It is the acknowledgement to our director CSR Siri, who has helped us and motivated for such kind of actively involved in such kind of activity. All the PhD students and our team member, which are project team members, all scientific and technical staff members of our semiconductor area, CSR overall, and all the sponsoring agency for their financial support. Another which I did not mention but I forgot to mention, sponsor those who have given us signs to share our experience, to share our work with all of you, and listening to us patiently. Thank you very much.
Any question? Quick question. Students? If there is no question, let us thank Professor Mukhia for his nice talk and very extensive work on this area. And let us thank the next talk is by Dr. Govind Gupta from National Physical Laboratory, Delhi, and he will be talking on development of highly responsive optoelectronic devices based on semiconductor heterostructures. Let us listen to him, Dr. Govind.
Okay, let me first thank to the organizer for inviting me to this conference. And thanks to the previous speaker who has changed a little bit from thermoelectrics to materials. Okay. So I will be talking about the development of highly responsive optoelectronic device based on semiconductor heater structure. So these kind of devices are basically we are targeting for the application of optical wireless communication. And you know, optical wireless communication is kind of optical communication where unguided different optical radiations like visible, infrared or ultraviolet radiations light are used to carry a signal, and these signals are being detected. And depend upon their range, they can be, these optical wireless signals can be defined in visible range as VLC or free space optical systems, FSO, which use higher frequencies, and other, especially in recent past, devices where UV based radiations are being used, where wavelength is varying in 200 to 280 nanometer. There are enormous application of these devices in military space, including intersatellite deep sea link. So as I mentioned, they can be defined based on their wavelength, ultra short range, medium range, and ultra long range optical communication. Recent past, Mitsubishi has developed a device for these optical wireless communication. And if we see what is there in the heart of this device, the device is consisting of a photodetector. It's at the heart of this device. And we know the photodetector is a key device in the front end of the optical receiver that converts electrical signal, which converts the optical signal to electrical signal. And you collect that electrical signal, and then you can measure this work as a converter. These semiconductor photodetectors are normally called as photodiodes and can be used for optical communication. So this is a schematic which shows that how the optical signal can be converted to electrical signal. And in semiconductor, the light is falling and then it's generating excitons. These electrons are transported to the conduction band, and holes are moving towards the valence band, and then we separate them out, and the charge are separated going toward the electrode. The current is achieved. So the sensor of light is photodetector. Now these detectors are also being used for optical data streaming up to 10 gigabytes per second. There are recent reports of where people have used different material like graphene is one of the material to transport this information. The other material like oxides, where different oxides are used and shine by different optical wavelengths from blue to green to red to carry information. There are SNS based hyper effective broadband photodetectors. This is also another area where people are using broadband photodetector. What is the meaning of broadband? Let us, I will just give you an example. This is a available commercial silicon photodetector. You know, in semiconductor physics, silicon and germanium are the basic semiconductor. Silicon is having indirect band gap of 1.1 electron volt, which is falling in the IR spectral range. And if you see a detector which is developed by this silicon base, the responsivity of the device is very high in the IR range. And when we are talking about the performance in UV or visible, it is not that good. And if you have to use a detector for UV detection, in that case, you have to apply certain filters, which will also, the UV also is having a lot of heat. So you have to provide heating compensation as well as a lot of other damages. So silicon is commercially available. We want some kind of detector which can detect these radiation in the broadband. Applications are enormous, in spectroscopy to communication, from medical imaging to alignment, laser rangefinder, or so on and so forth. So what basically is the basic criteria how you are going to develop a detector? If you are going to develop a detector, it should be stable first, robust. It should have low noise equivalent power, very high responsivity, high detectivity, fast in response, reliable of course, and ultimately we want a device which can work by itself. We don't require any additional power circuitry or additional bias voltage to the device. So these are the basic requirement, and these are the criteria by which one can test the quality of the detector, like quantum efficiency, responsivity, spectral response range, which is defining over which range spectral optical range is working, noise characteristic and response time. So over the period of time, there is a lot of innovation in semiconductor based material and device, which help in fabrication of detectors. Depend upon their band gap, they can be categorized in different segments, from deep UV to vacuum UV to UVB, UVA, visible or IR. These are the material. And if you see carefully, there are material like oxides, there are material like nitrides, there are recent development in the semiconductor like 2D materials. You might have heard of transition metal dichalcogenide, which where their band gap can be tuned depend upon the number of layers. So there are various kind of semiconductor materials are available. I will be talking about the nitride based semiconductor materials because this is our core area. And then nitride are basically group third metals, and nitrogen group fifth is called third fifth semiconductor. Group third metal like aluminum, gallium and indium. If you choose any material from group third like aluminum, if you choose, and nitrogen, it is forming aluminum nitride. The band gap is going to 6.2 electron volt. When you are going indium, it is going to 0.7 electron volt, and for gallium nitride, it is going to be 3.4 electron volt. If you check carefully, we are talking about 6.2 electron volt to 0.7 electron volt. It means we are talking about the entire spectral range, not only from optical electromagnetic radiations, it is going from deep UV to far IR. So, depend upon the alloy composition, one can tune the band gap. If you compare with the silicon established technology, high electron mobility is there. But as far as nitride is concerned, if I will talk about the simple comparison point of view, gallium nitride, it is having direct band gap, high radiation hardness, excellent temperature tolerance, high absorption coefficient, and if you can change the composition, alloy composition, you can cover the entire spectral range. Here, if you see, silicon is falling only in this line here. In this line, while nitrides can cover the entire spectral range. And these material also fascinating. 2014 Nobel Prize is given to these three gentlemen for their innovative approach to develop nitride based LEDs, which we are nowadays commercially using. And in fact, they got the Nobel Prize on the basis of the commercial impact of this innovation, not because of the scientific innovation, on the commercial or technological impact. So if I see the commercial market point of view, what is the commercial market? Because there are enormous technologies, research and things we are talking about, but they are not going to the market. Ultimately, if I'm talking about the gallium nitride based LED, every cell phone nowadays is having nitride based LED. All the high power LEDs, and even the market, this room is also having a lot of LEDs bulb. So if you see the nitride based device, CAGR is expected to go by 60%, and the target area is consumer, telecom, datacom, automobiles, industry, energy, defense, aerospace, so on and so forth. There are a number of things. However, the nitride based optical detectors are in the initial stage of development. There are few where responsivity is not that great, so we have started working in this area. Now this is how we are working, and then these are the research activity of my group at CSR National Physical Laboratory. We grow epitaxial gallium nitride films, nanostructures and heterostructure by plasma system molecular beam epitaxy, which is one of the highly sophisticated technique to grow any epitaxial thin film across the domain. Then we grow metal oxide thin film nanostructures by sputtering, thermal and CVD. Then metal chalcogenide thin film van der Waals heterostructure. Then using all these material and form their heterostructures. to cover the various optical or spectral range. The device fabrication and testing with solar blind and visible blind UV detectors, broadband cell power detectors, ultra sensitive gas sensors. And recent approach we are talking about the quantum devices, and there one point is missing is light matter interaction we are extensively doing. So how we are fabricating these nitride based detectors? By using state of the art plasma state molecular epitaxy, which is one of the high end device, high end system, where you can control the monolayer thickness of the material, their doping, their composition. So it means you are doing band gap engineering, you are doing the interface engineering, you are doing the dope engineering. So you can do n number of things with this kind of machine. We grow up to 3 inch on silicon sapphire, silicon carbide substrate. They grow different kind of heterostructure. The TEM is showing that layers are, atoms are arranged in periodic nature. There's a lattice you can see. Then we do a lot of characterization using XRD, photoluminescence, and other. Then we do a lot of characterization in terms of electronic structure using X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy, and then device testing and fabrication. So this is all about. So now I will go quickly to some of the things which we have done in last 3-4 years. Then I will go a little bit fast what we are doing in last 1 or 2 years. So this is what we have started with gallium nitride, because gallium nitride is a material which is having enormous possibility. At the same time, this is a material with where you can do many things. This gallium nitride is to grow on C-plane sapphire. C-plane sapphire. Sapphire is Al2O3, and then C is orientation of 0001 axis. And when you grow, it can grow either in the gallium termination or nitrogen termination. We can say gallium polar or nitrogen polar. Gallium polar and nitrogen polar is when we are growing metallic rich or nitrogen rich condition. In that case, the performance will be different. This particular device is grown on gallium polar gallium nitride, and by tuning the condition, one can also change the threading dislocations. Gallium nitride is not having any basic substrate on which you can grow. When you grow on a different foreign substrate, the defects are bound to happen, and this is the beauty of the material. Defects are there, and because of defect recombination of at the defect site, the light is being generated. So you can see highly responsive LEDs are there. So defects are there. So one can also tune these dislocation or defects. Depend upon the dislocation defect, this device was fabricated. Then we have analyzed the impact of substrate orientation, where by choosing this different substrate like C plane to A plane, how the device is performing, and you can see the IV characteristic tells that C plane sapphire is showing omic behavior, while A plane sapphire substrate is going towards the Schottky behavior. So then multi-layer structure is showing different pathways. When you have structure where electrons are transported from one side to other side going through the material, then in that case you have no barrier. When it is going through different barriers like aluminum nitride or so, it is having double barrier, triple barrier. Depend upon that the device is performing. Then another one is electrode engineering, because when you are growing electrodes also have an important role, because their work function is playing a role. So we have studied the impact of these metal electrodes, and different metal electrodes are showing different behavior, and ultimately charge collection efficiency is observed to be higher in asymmetric electrodes like PTAG or so. The most important one was this one, which we have published in 2017, became one of the highly cited paper in applied physics letter, where this non-polar gallium nitride, which was grown on R-plane sapphire substrate, and this was the highest responsibility which we have observed of 340 milliampere per watt. At that point of time, now we have moved up too much. Then, as I have mentioned, the silicon is a commercially established technology. we have used silicon as a substrate. Silicon gallium nitride having lattice mismatch of 17%. It is like if there is a space of 100 seats in this room, and we ask you to accommodate 117 people. Then 17 people try to create a lot of stress. So this stress will ultimately leading towards the dislocation of the device. To reduce the dislocation or stress, aluminum nitride buffer is being introduced in the gallium nitride film, in between gallium nitride and silicon. So this, which the impact of aluminum nitride on gallium nitride device was studied. Before that, we have studied the gallium nitride nanostructures. Ultimately, the dimension of less than 50 nanometer or so. Then slowly growing the film. Because of dislocations, you can see these films are not complete. These are 50 nanometer or so thin films. If you increase the thickness, then only the films will start completing. And then these dislocations which were going through the film, we have tried to accommodate and then utilize this dislocation to work as a template to grow nanoflowers, to increase the large surface area. When you increase the large surface area, the photons which are coming to the surface of the material, they try to interact more and then develop more photogenerated charge carriers, and ultimately we can see the device performing well. And here at 1 volt bias for this nanoflower based device is showing responsively 10 to the power 10.5 ampere per watt with detectivity in 10 to the power 10 joules. And if you see carefully that the commercially silicon based device is having 0.1 ampere per watt. Here we are talking about 10 ampere per watt responsivity at 1 volt bias. And in fact, this device is also able to give very good response and even no applied bias with responsivity of 132 milliampere per watt with low dark current as low as 95 nanoampere. Now, as we know that there are a lot of research is going on in different material where metal nanoparticles are being used to generate or used to interact with the optical light, generating a local surface plasmons. So we have also utilized those gold nanoparticles to analyze the impact of these plasmonic structures on the grown gallium nitride films. And one can observe that gallium nitride nanoisland is showing enhancement in photocurrent by 10 times. Then nanoflower is showing enhancement in almost 3 times of bare gallium nitride. So I will be quickly moving to next part. Another one is the innovation engineering in the growth of gallium nitride. So to increase the large surface, to increase the surface area, we have grown this kind of film where aluminum nitride, we have tried to tune the aluminum nitride quality, and because of that the film thickness is changed, and impact of those aluminum nitride buffer can be seen in the gallium nitride. Ultimately, while we are growing, we have reduced the flux and then grown taper-like structures. You can see this is a cross section SAM and top view of these nano towers, and utilize to further increase the area. Zinc oxide material is used, then oxide nano rods, which are also having a band gap in the similar range of 378 nanometer or so, and then utilize gold nanoplasmonics on top of it. So we are using 3 impact. Now, when we are talking about gallium nitride, then on top of it zinc oxide, on top of it gold nanoplasmonics, we are generating number of interfaces. When we are talking about interfaces, the transport of charge carriers is very poor, I would say, because you have to cross the hurdle. One hurdle is there, then second hurdle is there. But because of the structure, light matter interaction, you are generating more photons. So photo current is higher. But since there is a hurdle, the response time is delayed. So we are able to enhance the photo current maybe 10 times You can see here, this is 2 milliampere to 27 milliampere after going to different stages. But when we are talking about the response time, I'll skip all those parameters because time is limited. And responsivity, we are able to achieve 7,000 ampere per watt, which is the highest we have reported. So response time, which was we could be able to get in microsecond, is going in towards in millisecond with number of heterostructure. So this is a disadvantage of adding something on top without epitaxial nature. So now to address this issue, we have tried to form 2D, 3D structure using 2D materials. This is 2D materials like graphene, hexagonal boron nitride or MOS2 or so. These 2D materials have very strong bonding in plane and very weak bonding between the planes. You know, the band gap can be also be tuned depend upon the number of layers. The advantage of 2D, 3D heterostructure is the first one is gate tunability. The doping can be controlled easily in 3D and no interface engineering required in 2D material. So if you are going to develop 2D, 3D heterostructure, these are the advantages. So we have utilized this recipe to fabricate different structures. When we are talking about the 2D material, we have utilized MOS2 and bulk MOS2 band gap is 1.3 electron volt. As you keep on reducing number of layers, you can see the band gap is slowly increasing and from indirect to direct became direct, and the band gap reached to 1.8 electron volts. Absorbance is also increased. So we have fabricated this 2D MOS2 3D gallium nitride broadband optical detector, but before going to study the device characteristic, we have to understand the physical property of this material, what kind of interface it is forming, what is the structure, optical behavior, absorbance, and so on and so forth. This characterization will tell you like the absorbance is slightly increased because gallium nitride is having impact in UV, absorbance in UV. When you are using MOS2, it is going towards the visible. So we have utilized a material which is having band gap in visible and the material which is having band gap in UV. So absorbance we can see increase. The device is characteristic going from near ohmic to Schottky, and the optical characteristic is showing the presence of MOS2 also. Once you are making these heterostructure, you have to also see what kind of band alignment is there. So for photo detector point of view, type 2 band alignment is required so that your charge which are generated on one side or the other side, they can be transported easily. So for that purpose, extensive X-ray photoelectron spectroscopy analysis was performed, which is showing type 2 band alignment is formed between MOS2 and gallium nitride. These devices were tested under the influence of different optical radiation starting from 280 to 850 nanometer. The bare gallium nitride based device is showing very good response of 280 to 365 nanometer optical illumination. But while testing this bare device under 455, 565, 850, which is coming from visible to IR range, the device is not responsive. While MOS2 gallium nitride is responsive to all 5 optical radiation, it means we are getting UV to broadband in this particular device, and the response is clearly visible in terms of photocurrent for bare and MOS2. Besides this, if you can see carefully, like the photocurrent is also enhanced by 6 times in UV range. So that shows not only the device is showing broadband, it is also increasing the charge carrier, which is because the dislocation, which was the major cause of transport. Okay, major cause of transport, major hurdle for the transport is being passivated with the presence of MOS2 in this. So I have to go quickly. I have only 1 minute left. I have 40 more slides. So I will go quickly. No problem. So this is basically the responsibility or other performance parameter. I just wanted to give you an idea what it tells. It tells if you have a material which is defective. Sometimes कहा जाता है कि खोटा सिक्का. Gallium nitride used to be a खोटा सिक्का when it was initially invented in 1970s, and people used to say this material is not worth. It became highly serial material after 20 years. So even though those are sometimes हमारे parents भी हमसे कहते हैं ना कि तुम कुछ नहीं कर सकते, you should not believe on that. You should believe on your values. This by seeing the gallium nitride, and now even it is also giving support by the help support from other material. This material is becoming more and more advanced in terms of material device performance. Nowadays, you can see quick chargers are coming. You can see your phone can be charged in seconds. It is because of the power of the material. And thermoelectric also characteristic, but the power of the material, how the charge can be transported, what is the current carrying capacity. So this is basically depend upon the material. So ultimately, it is the idea by which you are making innovative engineering. What is at the core is the material which is defining the property. So this is all different application. This is one I just wanted to correlate. I'll take 2 more minutes. My student was trying to, because when you are playing with the machine and you are acquainted with the machine, though machine is costing us 15 crore, they try to utilize time. So they try to change the different flux. So they have developed this kind of structure, which is will later on try to correlate to become the Gaussian pyramid, which is having large surface area. Large surface area ultimately leading towards not only for large photon absorption interaction, but ultimately because bare gallium nitride having this kind of structure, it is also stable up to 250 degrees centigrade, which no photodetector has shown till now. With a high responsibility in 10 to the power 5 ampere per watt, with response time in microsecond, we are able to get. I'll go, and then students are expert now. They are growing cocoa palm type of structure on top of the previous pyramidal structure, broadband with high responsibility, stability, but room temperature 250 degrees centigrade. Very good, quite transport characteristic, performance parameters. Other material also tried, like SNSE or so. There is also material which is also showing, and we have increased the band from 850 to 1064 now, further broadband. Now we have gone up to 450 nanometer. So we are going from deep UV side to 400. This again gallium oxide is another material for deep UV application. The new one is because when I used to give a presentation, there are many people used to ask, you are growing on 15 crore machine. Why don't you grow with lower cost machine? Why don't you try with thermal evaporation method, which is costing you to few lakhs rupees? So we have tried with thermal evaporation. So we have to choose a material which can be evaporated by thermal and can be very high quality. So we have utilized this SP2 SP3 with thermal evaporation method, and this is showing enormous performance in visible range. This very simple method, we are growing microdots and then finally growing in the thermal evaporation. Device stable. I would like to summarize here. Thank you to the chair and co-chair giving me additional time. So these are some of the things what we have achieved. There are few publications. I have. This is my duty to show the hard work of my students. They are working day and night, and even last month, 2.5 months, we are able to get 17 publications from our group in this year itself. So these are some publications from my group. Since we have started growing in this area, these are the facilities at my lab. We have not only the state-of-the-art growth technique, we have X-ray photoelectrospectroscopy, ultraviolet photoelectrospectroscopy. Then this machine includes 11 other techniques. Then we have optical characterization. This is one of the state-of-the-art photoluminescence, which is having 5 lasers with entire range from 230 nanometer to 1600 nanometer with the low temperature to 10 Kelvin. These are other deposition techniques which we have. Thin film characterization, gas sensing, photo sensing. This is another duty to thank the director, student collaborator, all funding agency and all the agency, those who are supporting or giving kind of platform to say our things. Thank you very much.
Any question? Quick one or two question from the students?
I try to finish in my
Yes,
2 minutes.
yes.
So coming on to the application, very nicely covered talk. I must compliment you for that, sir. So, are they in condition? Can we use them in free space optics communication, because we are facing similar issues in, because we have requirement wherein graceful degradation is one of the parameters which we are looking at, because thermal sensitivity as well as thermal stability of these devices. Once we operate them at 40,000 feet, the FLIR image goes for a toss. And we need that data in real time so that we can have our informed decisions.
We have limited funding and we keeping the application as a target. We are developing device, testing in the laboratory condition. Okay, and the device are showing very good result up to 250 degrees centigrade with enhancement in the dark current, because of it, obviously it will increase. The photo current is slightly reduced, so we can see from room temperature to 50, there is a change in the optical current by 30% or so. But we don't have that kind of acceleration procedures or technique to test this. So if there is a requirement and we can work, so we can try and give a shot to work together and see the application part.
So thermal is one part, you said plus 250. You talk about minus 40 also the same time.
We have not tried, but definitely I am telling you, gallium nitride is a material which can go easily withhold and not show any change, because we have gone down even 2 Kelvin. It is showing very good responsivity under CCR cooler. This is a very good transport material. Semiconductor, very good transport material.
Right.
So if there is a opportunity, we will help and work together.
Right. Thank you.
Any other question? If no question comes from the student side, then I will feel like I have not ignited their mind.
Okay, if there is no more question, then let us thank the speaker for so much work on this optoelectronic devices and based on semiconductor heterostructure. Of course, they can take it as assignment for their project. They can do on this photodetectors.
If somebody is really interested, they can come to my lab, work for 6 months or 2 months, summer research fellowship or so. So you are most welcome to work. There are 10 students from different laboratories are working in my lab right now.
So the next talk is on magnetocaloric materials, that is magnetic cooling for green technologies, and this is by Dr. Vasundhara Murtha, and she is principal scientist, polymers and functional materials, CSR Hyderabad. And you have time to do this.
Good afternoon to all. Thank you very much for the introduction. Actually, I expected some bigger audience, and that doesn't mean that you are a smaller audience, but here I see the mostly students. And today morning only Professor Sharma told about this, then I changed my talk. The second thing is that afternoon I saw many of you have learned about the thermoelectrics, so some of the fundamentals. So I'm just giving here something related to, am I audible? This mic is required? No, thank you. So I changed my topic, and And this is also a cooling only, about cooling technologies, but it is about a magnetocaloric freeze. I would like to, in 20 minutes, I would like to finish the talk as per the JHC audit. The talk is on magnetocaloric materials. It's a magnetic cooling for green generation. Next. First of all, Sir Professor Gupta, he has left. Did he tell anything about CSR? Then I will tell, otherwise I will skip this one. First of all, I would like to tell about the CSR organization. It is one of the oldest organizations in our country and one of the biggest also, which is having it was established before our independence. Many of you who are aspiring for doing PhDs, I am sure that you know CSR because of the fellowship. It not only offers the fellowship, it also offers travel grants and some projects from the different universities and funding agencies. And another important thing is that I do not know whether you have heard about ACSR. Now, it is an Academy of Scientific and Innovative Research. This is the only universities which is Parliament of Acts. It was passed. So it is in the, once you join in a CSR laboratories, you can register for PhD in this. This is a virtual university. And for more interest, you can just go to the website. Just cross that. So this is an organization containing 37 laboratories. It is a chain of laboratories with a different expertise, which is started from Jammu to down south, Thiruvananthapuram, and in east it is at Jorahat, west it is in Gujarat, the labs. So each labs are specialized areas. It is having right from the beginning aerospace engineering to metallurgy, and then the leathers, for which is a central CLRI, that is Central Leathers Research Institution. So each organization is specialized for certain activities. Then these colors you are seeing, these are all distributed amongst 5 different clusters, which is the biological sciences, physical sciences, chemical sciences, and engineering sciences. So then how these are all works and all, it is a deep intricacies. I am just showing you, you must have heard recently during the one popular thing about the COVID vaccination. That is most of that is Covaxin was developed in CSR ISCT lab. Next slide. This is located here. It is in Hyderabad. We have 3 laboratories. One is ISCT with different clusters. ISCT, this is the lab where it has, along with the association of the Bharat Biotech, it has been developed. So it is having a total about 10,000 employees, where out of that 3,500 are the scientists. Rest all are other supporting staff. So please consider. This is the site of the location. Please next one. ISCT is having a 469 employees, out of which around 160 are the scientists. Please next. Yeah. Now coming to the present talk. The present problems due to the current refrigeration techniques which you use, that is based upon the vapor cycle, it's a thermodynamical phenomena. You know that it is some gas, compressor gas that we use. So what it is the important present scenario is as per the climate change and then issues based on the present global warming situation, which you says that the Mother Earth, I think you must have heard about several topics recently that global warming is increasing and it is one of the highest threat to the humanity. It is more dangerous than the terrorism because it is increasing day by day. The things are happening because we are using the more energy. We are consuming now. How many of you are here but AC? And everyone we are using luxurious life, cars, so many things. So these are all, it is going into the gases because all these, out of that mostly the cooling systems which you use is household refrigeration and then AC. So this is around 30% out of this refrigeration system base which is using, that is efficiency. So this, what it is getting, the temperature is changing because of the gases which you use. Some of the gases are very harmful to the, that is enhancing this thing. So out of this today's refrigeration system accounts for the HFC accounts, that is 10% of this global greenhouse gases it is affecting. But out of that, what I mentioned, the refrigeration alone, it uses the 20%. That is, it is accounting to 20% of the global electricity consumption. So next. upon the data of the international refrigeration thing. So then there is an alternative to this, whether do we have it? Yes, there is a, it can be used when there is an alternative technology which we can replace the current system. So this is a, what is a magnetic refrigeration? It is the concept and the proof of concept and the technology is well established. It is developed, but the problem is that it cannot be used because it is not economically viable to replace the current systems. Why? Then you need to understand a little bit more. I will explain it in a committee. So what helps it is that one, it is definitely environmental friendly. It does not need any electricity. I mean, for that electricity, other components, but for that purpose, which makes it cooling, it doesn't need the electricity, and it is a better energy efficiency. As per the statistics, it said it's a 40% more than the current based systems, currently used vapor compressor based systems. Then it has a better adaptability and it has a long life because it is not based upon the gas, it is based upon the solid state systems. So how it affects? You must have heard this definition, magnetocaloric effect, thermodynamics when you get this. What it is that certain materials have a ability to heat up when you keep that material under a magnetic field. Similarly, when you remove that magnetic field, then it has a tendency to get a cooling. That concept is called the magnetocaloric effect. It was invented days back in 1881 by this gentleman, but later what this the concept which was practically understood by these two scientists, then they have told that this magnetocaloric effect, it can be used for the low temperature to decrease the temperature in the process. That is known as a adiabatic magnetization. So how it works about it is, okay, the next slide I will explain it. So this is a gas-based refrigerator and magnetic refrigeration explanation. So here what we are using here, expansion valve, that means here the importance, the thing is it is a gases we are using. Here it runs with the 4 cycles. Once when it goes to the compressor, then it just heats up the material, and what it happens, it takes that material back and transports to the that substance which you needed to wanted to make it cool, and then that cooling it goes, then expands, then the cycle it goes similarly. So the similarly one-to-one analogy when you just use it, here instead of the gas you take a magnetic material. So when you take a magnetic material, in the morning I need not to explain the fundamentals, Chandra has explained that about the magnetic spins and all. So this is the material when it is not magnetized. So when that material you keep it under a magnetic field, then what will happen it takes more energy to align that one and it gets up heated up. So then that heat you expel it and take the material under that adiabatic conditions, that means Q equal to 0, without that material, when you just take it out, the system expel the heat. After expelling whatever the material you have, that material you keep in the substance where you wanted to keep. Then that material under the thermodynamical conditions you need it remove the field. Then that feeling cold, it gives the something temperature down. That temperature you use it for the cooling the substance. So for example, at 30-degree room temperature, some material will keep it. Now first one cycle, that material can come down to 1 degree, then it comes down to 29 degree, then slowly subsequently you can bring it for several cycles 20 degree. If you want your sample to be the fridge or something else which is required for that 20 degree is enough, then time cycles the sample it can be keeping that. So that cool, this is a concept you can utilize for the purpose. Please go to next slide. So this is a quantitative analysis in a quick to understand as a layman. You are not going into the deep intricacies of the mathematics. So this is a thermodynamical phenomena. So there are 2 quantitative analyses to judge this material, whether this material gives enough cooling capacity or not. One is called isothermal entropy change. This is based upon the Maxwell's equations. One is the magnetic isothermal entropy change, and another one is adiabatic temperature change. So generally what happens that this material where it gives the huge changes in the the temperature is, the material when it has changes in phase transitions. Okay, so phase transitions also there are two types, first order and second order. First order means what? State change. So state we are not changing here, so it is a second order. So the second order transitions where it has a now it depends upon the which temperature range the change is there. That temperature you will be able to cool the things. Suppose your sample is changing the phase change around at a 30 Kelvin or 10 Kelvin. So are there any human beings using at that temperature that refrigerations or something? But there are certain other applications. But the mostly what we are using and when we wanted to take this technology as economically viable, that is for room temperature applications unit. So mostly out of this, which I explained, 40% is post consumption for this our household items. Then to have this material for the required capacities, the material should have a large this ratio. That means the sample should be strongly responsive to the magnetization with a small magnetic field. The small is the field, the small is the you need capacity of the magnet. Then that tunability, this depends upon the applications. Then the material should have a softness. It does not need to have a large instances to avoid the energies. So a system which undergoes there are many systems. You heard morning ma'am told about the spinner type structures and some two-dimensional structures that he has explained. So the system which undergoes magnetostructural phase transitions, so that generally involves a magnetokinetic effect. So next slide, please. Yeah, so this is one of the medical magnetic refrigerator was developed in years 2016. It is in a commercialized, it is in a cool tech applications, but this is for the low room temperature applications only. For magnetic medical refrigerator was developed. So please just to show that. Next please. So how this technology has come from that end to this end, I'm just going quickly. In 1881, what I told about the concept has been done. Then later these two gentlemen has developed, and in 1949 for his work he got the Nobel Prize. Then after so many, nearly 5 decades later, in Ames laboratory they have made this proof of concept with the material using gadolinium. Is the gadolinium as a magnetic refrigerant material. Then afterwards there are many, it was every year, almost every alternative year there were several refrigerator in news. It has come even in this again in America, and this is in a Danish laboratory, and then magnetic again in a Caltech they have developed. Now later in this to freeze some lower temperatures like liquefying the helium gases also, this has been used. So the main important things of this developed till the date, whatever the developed refrigerations are, it can generate around 400 watt of this refrigeration power, and it can keep the internal temperatures between 2 to 5 degrees centigrade for this simple material. So that means this temperature, the more temperature down you want, the more number of cycles it has to undergo to that one, which I had explained in that topic. Then it has required a minimal maintenance because low operation cost. There, like for a compressor, you need electricity to do that. For this magnet, you do not need any electricity. You need some piston, mechanical piston to pull and push. That is there. So there you can save some electricity. And it is, of course, it's the things you can see when compressor turns on, turns off. You hear noise, right? Here that noise, it will be issued. It will be lessened. So as of now, until 2019, this is a huge number of patents. This is the database of 2019. Huge number of patents has been issued in this one, in this topics. Next. So now this is the basic introduction. Now I'm just telling about what all the state of materials, state of art of materials existing, which can show for the magnetocaloric effect in this. So there are a variety of number of around total 12 families of compounds are listed here, which shows the magnetic entropy around 40 Kelvin. 40 is the figure-mate, which is different, but in the different temperatures ranges. But out of that, you must have seen all the materials which are showing are based upon the intermetallics. There is only one material, one family of the compounds which are oxide-based systems. So even though the intermetallics are having a higher power, in the lower varies from the 100 Kelvin to this 300 Kelvin, 300 degrees Kelvin temperature. But we in this talk, what I have chosen, we have chosen is based on a manganate. So I will tell that what made us to choose this particular materials. Because how many of you are know, but to develop an intermetallic system, see, you need a huge infrastructure. The things are not that easy. It is highly expensive in comparison to the basic oxide systems. Amongst this, the best materials out of this choice is where this is a gadolinium based sample. Gadolinium is one of the most costliest rare earth elements available. Then it is a manganate. This is again the intermetallics, but without rare earth. These compounds also are giving a very promising value of the temperature. Here onwards, I am telling SM as the temperature span, which can give up to 1.7 Kelvin under 1 Tesla of the magnetic field. And the required temperature is also 300 Kelvin, which is very near to that. But this has some problem. Arsenic and phosphorus are very much toxic, so these samples cannot be used for the practical applications. So out of these things, we have chosen this material in spite of having a lesser one, and the temperature is having a much higher, around 70 Kelvin, 70 degree temperature, higher than the required target what we have had. But what made us to think is that these materials are very cheaper. This next, in comparison to the intermetallics, these are all expensive, but these materials are very low cost and in laboratory very easily with using some very less infrastructure we can develop, and they have a higher chemical stability in comparison to that intermetallics, and also these samples have a least magnetic distances. Next, please. Next. Now, one of the challenges is to make the inexpensive raw materials. So, inexpensive raw materials, we have a rare earth. I will explain it before going to that things. What is a perovskite? Perovskite, generally it is this generic formula AbO3 crystal structure, where A is having a rare earth elements and B is having a transition element. If the transition element, suppose it is a manganese, it is called a manganite. If it is you are having an iron, then it is having a ironates. If it is a vanadites, you must have heard about vanadites, chromates, and all. It has a huge number of applications, right from the solar cells to in the medical applications also, but for biomedical applications also, these materials. This one here, there is one small chemistry which is important. I will explain you. Here you see AbO3. A is a rare earth element where the oxidation state which use it is a 3+, and B is also a transition element, that is also 3+. Here I spoke about manganese, that means it is a manganese. So manganese is a 3+. In order to make the charge neutrality, what it is, this is a -6 oxygen. So this is a very stable compound it has formed. Now, when we dope with some alkaline elements, so because the requirement is there, doping, I will tell in the next slide. When you dope these alkaline materials, what is this oxidation state? It is a 2+ state. So when partial replacement, it happens at this rare earth site, which I mentioned, 3+, when you partial state of alkaline elements, what happens? There is some charge neutrality it happens. Because of the presence of a 2+, what it happens is material, the manganese side, it splits into the mixed valency in order to compensate the charge neutrality. So whatever the percentage of the rare earth alkaline material you put, the corresponding Mn 4+ state it converts. So that 4+ state, that creates a mixed valence. So that is why these materials are popularly known as a mixed valent manganites. So here what happens, when the parent compound, it is the property, I am just showing the same formula, one end to another end properties are there in compared to magnetic and transport properties. Magnetically, this compound is mostly, these compounds are antiferromagnetic and highly insulating materials. But a little substitution of this alkaline materials turns this material to be a ferromagnetic. It is strongly conductive. Time is over. I'll finish it. Okay. Next, please. So why here? This is already in the records, the literature. These are all the compounds when we take. This is at around a 0.33 concentration. This gives the best deserved properties. That means the magnetic entropy is also reasonably acceptable, and the transition also it comes with 300. So that is the reason in this materials mostly every material of ferromagnet which shows the magnetocaloric or the interesting transition properties, you must have seen huge number of publications in this material. It is getting published. So you can see this particular composition. This can be anything, this can be anything, but this composition is there because at this particular concentration, the mixed valency ratio is 0.67 to 0.33. That is leading into the magnetic entropy change and the transition, the desired magnetic entropy change you get it. Next. Next, please make it faster. I'll just. Yeah. I think one missed. Yeah, this one. Upper also, one more please. One more please. Previous one. One important thing I want to, okay, fine. So here, I don't know, slides are missing, but here we have taken this material which is already reported 373 and my fourth slide I have shown it. Then what we have done here, we have not added anything else. Sometimes the defect mechanisms plays an important role. So what we have done that one, we have made a small defect at this lanthanum site and then strontium site. It is around, you see, 0.09 values. So then what happened, when we made the deficiency in this compound, so we got this transition temperature from 374 to 352 Kelvin without reducing the required magnetic entropy. Next, please. Next. Yeah. So what made this one is that we could successfully tune the transition temperature of this compound near the room temperature with an enhancement of 48% of extra of the magnetic entropy. So here the defect engineering we had helped us in tailoring the magnetocaloric properties in this compound. Okay, next please. Next. So yeah. So now the one more challenging what was that it was our 12 to 5 year plan project. So the demand was that to utilize the Indian resources. That was Indian rare earth elements. Then you know that Indian beach sands, there is a beaches. Monazite sand is available. That monazite sand is nothing but where the thorium content is there. So after the extraction of the thorium, IREL, which is Indian Rare Earth Limited, that is a part of a Department of Atomic Energy Organization. They extract the thorium and the rest of the materials they give it to the respective laboratories under that organization. That is a mixed rare earth oxides. So in the process of doing, there is previously I said only about the lanthanum compound, but when you do with the different compounds, so there are an unending, there is no end to tune the thing. You can see much more publications and all, but here the aim is to directly utilize those materials because which are having a mixed rare earth. So this mixed rare earth oxide we have taken from them. And we made this particular compound to check. And you see, this is a compositions of that, which is a cerium oxide. This is a natural composition which is available. So that's why I use the natural sand. Okay, next please. Then we made the same composition which I have told that this, but here instead of lanthanum, the rare earth mix we made it out. Then it got a simple perovskite structure, and all this analysis is to just show the industry people when we have done it has exactly formed. And but the thing is that here, instead of, apart from the pure perovskite structure, there is another impurity system also formed, that is the cerium oxide, which is no wonder because cerium has a more than nearly 50% of the compound it is there, and that we have analyzed, we have seen in the morphology also. Please next. Then when we made this compound, when we checked the magnetocaloric properties, we have checked all the required properties, then we saw that the transition temperature which was coming naturally down to 310 Kelvin, which earlier I have shown around 324, 310 Kelvin, and the temperature span which was the target, it was 1, but we reached more than 100%, it is 2.11 Kelvin it has, and then it is, the value is also at a 3.28, next please. Next. So then what was the one more thing, these two slides are last one. When we made that composition, when we had a discussion, we explained then that whether you are ever, ceria is not a magnetic. In fact, it is an antiferromagnetic. That means the word itself, it can kill the magnetic property. So when we told that when you have given the natural material, it has this much properties. But suppose, is it possible your chemical engineer can extract that cerium and rest of the compound, whether can they give it to us? We asked them. Then they said, because of your experimental thing, our engineers cannot work it. You show us a proof of concept that without that it can work. Then we have taken these are the commercial materials. We have made two set of materials, compounds. The same. This here rare earth mix means one is this set and another one is this set. This set is exactly mimicking what is the natural resources, and another set is without having the cerium to show them that this does not have any magnetic property. So when we did it both and we have checked the samples, next please, we see what it has happened. Both form the structures, but here the impurity is a very less, the secondary phase in comparison to the previous one, because previous one was a natural, it was not any, it's a raw material we have taken. Here also the secondary phase ceria is there, but the problem is here the advantage is the secondary phase is not even we could not even define it is lesser than 5%. But here the thing is that if it is not having a ceria, then another largest rare earth compound it is started forming the deficient. So there is no use of any separation. If suppose lanthanum also we remove, the next another higher concentrating rare earth element it was started having the secondary phase. So then further we studied all the studies. Next please. Next please. Yeah. Then we have done that. What we got is earlier we got around 3.28. Here we got around 4.22 is the work. And another interesting thing is that with the presence of ceria, it was higher than the without presence of the ceria. So we were telling them to do it, but it was not helping them. So their answers, in fact, it was helpful when we made it in a laboratory. So the presence of this material is, in fact, it is helpful in enhancing the magnetic caloric properties. Next, please. So this is what the thing. Then this entire activity, it took nearly more than 3 sponsors for projects we have to develop in our laboratory. Can you please next one? Yeah. So this is the prototype, the things which we are not yet generated, but this is the material when we prepare the oxide materials which are shown. Those materials we have to make in the form of this. It is around 10 centimeter cross 5 centimeter, and width is it varies from 0.5 to 1 centimeter. This sets up the rectangular shape. Let's nearly more. The more is there, the more is the represent capacity. This is what the size of the material which we made for making this prototype represent. With this, I would like to find that one with any other. Any question? 5 minutes more, I think. Yes, please. Area of yeah, that depends upon the the capacity, the way you use a bigger compressor for making a double storage and all. That depends upon that is an engineering aspect. We will not see that. What here we are aiming only the thing is this material. It is as of now we have shown to 2 Tesla. We wanted to reduce it to the 0.5 Tesla so that a small tablet it can be. Laboratory experiments we have done with the superconducting magnet, which is not possible to keep a superconducting magnet at home. So this is for the practical things, but that comes into the our target is to make it this a permanent magnet for even 500 host, not even 1 Tesla, 5,000 hosted we wanted that one. So that you can hardly get it for 80 rupees. Here in the Chinese market, 50 rupees you get it. So this is what the aim of it.
All are naturally occurring oxides.
That those are naturally means it is a sand that is called monazite sand. They extract the thorium for the radioactive purposes. After that is a natural occurring rare earth. But because of this 2010 after Chinese monopoly it happened, they also have a huge pressure from the government to make the separation of the rare earth. Because recently I visited in their industry in Aluva, located in Aluva, Kerala. Now, when 2015 I met, that time they did not have a technology. They were not separating the individual rare earth. But now they are selling it, even sodium oxide and all, and they are so confident that even, can you just show one that slide, previous slide? Then the smallest rare earth element also, they can, just next, down. No, you are going up, downside. Even the smallest rare earth element also, they can do it. But here one important thing I wanted to tell, that for the students who want to introduce. No, not sir. Yeah, okay. This is also okay. So here, this is a naturally occurring material, right? So see, here it is a ER volume. It is a 0.1. Is that much is a composition is available. They can do that. But what's the problem is that in order to extract this compound, they have to take this much of a compound out. When first they extract the ceria, they extract it. So in order to get it 10 grams of this lanthanum, now presently the project which I'm working, I require lanthanum and presodium. So in order to that, they had to 50% of the material they have to throw it. If you go in that Aruva things, by putting a stamp, red mark, that material is dying, because unfortunately that our Indian industries, they do not know how to utilize the ceria. So that is the reason they are not developing, but they are Indian chemical engineering scientists they are having enough capability to separate them in each individual elements, but only they are not able to do because of this thing. Where will they do? They are asking that please take some material. Even they started giving the projects also to make the utilization of ceria, because in LEDs and many optical properties they can utilize it. But that is the problem, that material they are not it, so they are doing it as per their requirement.
Okay, now we have sort of time, so if there is no any more questions from the students or audience, let us thank Dr. Vasundhara for his The last talk is by Commander Yogesh, who is senior engineer in aircrafts. He is going to talk on system design considerations for applications of thermoelectrics in defense aerospace ecosystems. He is not here.
Good afternoon, everyone. I am Vingamada Yogesh. Too less time to prepare for this topic, but because of my number of years which I have served in Indian Air Force, around 16 now, I am in condition to tell especially the lot who is sitting behind and whom we can instill our trust that they will understand what exactly the nation needs. So, it's a small presentation I've prepared. I would love to give my peace of mind to everybody that you should understand what exactly are the requirements of the research. Because if you do research in isolation,
then in that case it may not see a ray of light, and it may not be applicable for the intended purpose for which the research is being done. So this isolation needs to be removed at every level, and thanks to Dr. Yogesh sir that they've invited both of us. I'm also joined by one of my senior, Wing Commander Lubna. She's sitting behind, and giving us this opportunity to interact with all of you, the learned people, and understand that what exactly is being done in this research areas, especially in thermoelectrics and various other fields. So lateral absorption for us was quite high, and because we come from the field, we understand the technologies are being developed for various reasons, but do they have the practicality and viability as far as the system integration is concerned? So during my course of presentation, I shall be covering these topics. This is a general roadmap. I shall be covering and telling you about the inherent challenges of defense ecosystem. What do we face on daily basis as far as the absorption of technology and the applicability is concerned. And then I'll briefly touch upon the system design requirements. What do we require exactly for these technologies to be absorbed and adopted easily in the ecosystem, and some possible technologies which we can work on. Ours is a technology sensitive as well as the technology intensive ecosystem, sir. We have our systems. You must have seen Air Force is not all about aircrafts. If we talk about aircrafts, we have aircrafts of every type which you can imagine. It may be fighters, class of aircrafts from various origin of maybe from Russia and Western fleets. We have state-of-the-art transport aircrafts ranging from small India-made HAL Dornier to C-17, which is state-of-the-art, one of the biggest aircraft of its kind in flying in world. Similarly, we have helicopters, we have UAVs. I'm from the same fleet of UAVs. So this is just, you say that it's an aircraft. For us, it is a whole lot of fleet of maybe 30 different types of aircraft which we are operating. So imagine the kind of technologistics and technological challenges we are facing on daily basis to upkeep and maintain those machines and keep them flying for various mission profiles. We have different kind of guided weapon systems. When we call guided weapon, for you it may be a missile. For us it's a system with varied capability of hit range of maybe less than a kilometer till more than maybe 500 kilometers. So imagine the kind of technological differences and superiority these platforms possess, and at the same time the complexity they have in their system integration. We have host of radars which can look up to maybe from shorter distances or maybe till 10 kilometers till long looking radars which have a effective range of more than 1000 kilometers, which can look into Pakistan or the area of interest which may extend up to Iran or maybe beyond. Especially we apart from these radars, we do operate some special satellites also, and some geospatial analysis tools and everything. So image synthesis is an important part on daily basis which we do using our airborne platform and static platform and using satellites. So my whole point in telling all of you, all of the young budding minds over here is that you have to find out the applications and align your research topics in such a way that they find some practical application. And if it is viable, and the cost effectiveness has to come to that level, because as a nation, we should not say that we are a poor nation, but we are in that phase that we have to feed 1.6 billion people at the same time and launch some cryogenic based engine based PSLVs to prove our metal. So we have proven enough, but still in this defense ecosystem, we require some young bright minds who can come up with the idea and doing things and in pennies, because our dependencies on foreign OEMs is to that tune that it burns out a hole in our pocket and it burdens the exchequer. So development of these technologies in indigenous labs and laboratories with the people like you is the need of an hour. We have a host of ecosystem wherein the researches are being done, very beautiful researches which can see a ray of light, but because of the isolation of these systems, these researches are finding place mostly in the libraries, and they are not finding more into the practical real application, the prototyping. We are in a network-centric warfare scenario right now as we speak. And when I say network-centric warfare, that means all of the networks, all of the weapon systems or the sensors which we use are networked. So imagine the kind of data we process on daily basis, and the delay is unpardonable, because in our case the delay, I'll give you a slight example. If a fighter is operating in enemy territory, and if his imagery is not beamed on the right time, and or it has some data delay, even if of tune of few seconds, then the decision making by the commander who is sitting somewhere in Delhi can delay, and you can imagine it can be catastrophic, because our neighbors are sitting at a stone throw height of stone throw away heights, and from that distance launching a missile or an aircraft and hitting a vital target is a matter of few seconds, if I'm not wrong. So that means you can understand the criticality and the reliability of system which we require. That in network centric warfare scenario, a delay of even microsecond can cost us lives and even international phase. So that means our requirements are near real time. If not real time, practically it's not possible, but they are near real time, and redundancy and the reliability has to be 100%. As I've already told, the dependencies on foreign OEMs is so much that it is we have recently, in last 10 to 15 years, the ecosystem has built up. People are coming up with ideas. We have collaborative works going on with private players and universities of national eminence, and people are coming up, but still that ecosystem needs to evolve more. I'll give a recent example of Baba Mehar Singh Trophy, which Indian Air Force is running since more than third. We have entered in third edition, sir, and we have recently co-developed some good swarming drones in that thing, and we were actively involved in development of those systems, because what exactly we do need in our field, we know it by virtue of our experience in field. You may be knowing about the technology, but how it is adopted, if we both collaborate, then the adoption of that technology will become seamless. The rest I'll cover from my critical house, sir. So when I say about the system design considerations, then I would love to touch upon basic considerations which we need in defense aerospace in particular. Understand the application environment in which the systems are operating. You are posted at Thois, a place which is for around 120 kilometers further north to Leh. In the morning, the temperatures are minus 40. In daytime, they may reach sub-zero. And again, night, they will again touch minus 40. So imagine you have to build a machine which can sustain a temperature like that. And once that machine flies from there, it lands at Jodhpur, wherein you have 45 degrees temperature. So within a flight envelope of around 3 hours of flying time, your system is to be subjected from minus 40 to plus 40. So the gradient is 80 degrees Celsius. So for engineers who are working, or the scientists who are working on thermoelectrics, these temperature variations may be lucrative. But imagine the system, the thermal stress or the stress the system is going through during that duration. So the environment is very severe. It is vibration sensitive, because when you are flying in air, then vibrations, and because you are running on engines, they may be jet engines or maybe the rotary engines, so it is vibration sensitive. That means all the system, onboard system, the avionics is being tested to the peak of its capability, and the system reliability has to be that proven that it doesn't fail, because we do keep our safety of margin, that is usually 1:5, but still we see accidents happening day in day out. Afford to lose our machine, and first foremost men who are flying those machines. So the technology plays an important part, and the reliability comes on the forefront for deciding the machine how they will perform. The thermal swing, as I already discussed, is around 80 degrees, and it is done on daily basis. When you start an aircraft in the morning, it is around 40 degrees, and once you come back, you are already sitting on a turbine which has already clocked around 900 degrees Celsius. So imagine the system which is carrying the entire fuselage, it is already heated up around 600, 800 degrees Celsius, and the machine has already flown 2 hours, 3 hours or in long haul sorties around 6 to 8 hours. So that kind of reliability we are looking for in the system inherently. These intrinsic and inherent properties are to be incorporated in system design. Sir. We are looking at life cycle cost of almost 20 to 30 years, if not less. Because when we buy a system, they cost us a fortune. So the life cycle cost of the entire system, when we see the inverted bath curve tub, in that case, the usable life of that equipment has to be around 20 to 30 years. The warm to term life of that system has to be 20 to 30 years. That means again it translates into high degree of reliability and maintainability, so that the system can remain available for longer period of time without much maintenance issues. I'll talk about complexity. So imagine in my aircraft, Heron UAV, it is a 1100 kgs, only 1100 kgs flying aircraft, in which the total number of IOs, the input-output devices, or we call it ICD, interface control data, this is 10,000. So imagine at any point of time, 10,000 IO devices, IO signals are looming around in that aircraft to have that kind of flight characteristic and mission characteristic. So we have to deal with complexest of the complex avionics, in which and they all are intermeshed, interlinked, and cascaded. So even if intermittent failure is there of any system, it can jeopardize the entire system, and the results can be catastrophic. So the complexity of the system, over a period we have moved from a unitary system to modular system, but having modular system that gives you ease of system deployment, that if one system is down, you can just remove it and rack in the other system and make the system work. But that thing again poses limitation on the learning and the knowledge part of it, because if a system is down, you just remove it and push in, and that is what the foreign OEM vendors want, that they don't want our learning curve to broaden, and that's why they want us to be kind of in knowledge paralysis stage. So modularity, in one way, it helps us in keeping the machine, making it available for in a quick time, but in a longer run, it actually limits our learning process. So the complexity has to be in such a way that it can be addressed, any snag or the any fault can be addressed in near real time and can be easily diagnosed. But at the same time, the complexity has to be reduced so that it becomes easier to operate. We do have volumetric limitations. That means the weight is at premium, because any application which is on ground, you can add any weight, it doesn't matter, because for every weight, our turbine or the onboard power plant has to carry that weight, and for every gram of weight, the limitation is imposed onto the entire flight envelope, and that limitation may limit use of, or if the flight envelope is fixed, that means you have to somewhere compensate it, some functionality or some system. That means we have limitations in terms of volumetric. That means for catering that kind of power requirement, like if I say that we have a host of applications which we discussed during these 2 days, that thermoelectrics can be a very good answer for harnessing onboard power, which we have discussed with Yogesh sir also. But in that case, thermoelectrics, yes, it can be a very good source of power, but we have to see the gradient, how much power for how much weight we are getting. So that volumetric as well as the weight consideration has to be considered by all the researchers once they are delving into any specific research for aerospace applications. Cost would always be a benefit factor for us, because as these technologies are very price tag is quite high, and because the IPR part is not with India, so with in-house and indigenous development, we may come into a agreement on cost, that those costs will be obviously, as far as my knowledge goes, it will be maybe 1/10 or maybe even lesser than that, because of the IPR issues, we buy technologies, we have transfer technologies, and those kind of technologies cost us the fortune, I must say. So if you develop some indigenous technology which is cost effective, it would help everybody. Safety, I've spoken about reliability, so it translates into safety, because in aviation, in general day-to-day life, if your car develops some snag or something, you say ki side mein laga lo usko. But we don't have that luxury when we are in air. So in that case, the safety remains paramount. That means for that kind of safety, to ensure that safety, we have to go through a host of a series of thousands of tests for compliances and for proving that the system is safe and airworthy. So we have set up like Semilac, which is a lab owned by DRDO, which is into that certification of airworthiness of any system which is to be flown in air environment. So these are the basic consideration which I've told you about the system, which we look forward to when people like you design a system for aerospace application or defense applications. Some real-time requirements, like we have already discussed, that we do have consider that a turbine which is flying in air has got a differential of like we maintain our cockpit temperature in normal room temperature at 20-21 degrees Celsius, while at the same platform we have EGT, exhaust gas temperature, which are in tune of 800 to 900 degrees Celsius. That means in a single platform you have a this delta is around 800 to 850 degrees Celsius. So it can be harnessed entire chamber wherein the turbine is fitted is heated up. We, in case we have a turbine engine, we have exhaust gas temperature in tune of 600 to 700 this thing. We have some batteries which are on board, which are utilized for emergency backup in case the engine fails. So those batteries, imagine the batteries operating at in the comfortable range of, maybe though they are tested for minus 55 till plus 60, but their environment condition is minus 40. So once that battery is at minus 40, we have to heat it up using jackets and by other means. So if we are not able to, if that kind of power is required on board, and if that power is being generated by thermal material, then obviously it will reduce the overall burden on system, and that will be a onboard power which is not dependent on engine. So imagine if you can protect that battery, and in case the engine is failed, it is on battery, and battery is being protected by the Thermoelectrics. Imagine you can save maybe few precious lives and the system. So that is the kind of environment constraints environment we have when we are in air. So this is one. Then we have quite challenges in the clothing, aircrew clothing which we wear. So we have already discussed harnessing energy from the clothing which a pilot is wearing. Helmet mounted displays are at premium because we can't give them a power which makes them make the entire system bulky, and for a pilot mounting a helmet for 6 hours altogether and flying in that environment is difficult. So again, coming on to that the volumetric limitations and the weight limitations are less. If we can harness the power, even the ejection seat, a pilot is sitting for 6 hours, the temperature of his body can be regulated, because so that he can concentrate more, and his comfort level as in that comfort zone, so that he can concentrate on mission profile and not on his comfort. So these are some this thing. And when we are deployed in remote areas, we are operating with the small RT sets. Imagine a scenario wherein only 2 people are sitting somewhere hidden, so that they can't be spotted by enemy, and the any enemy aircraft which is crossing and somehow it is ditching the radars over there. So he is the first responder who can give you a call to the nearest node and tell them that I've just seen a F-16 who is crossing, and his attitude and his direction is not in a correct manner. He may cross within few seconds. So imagine if that guy fails because of the system limitation, his battery is drained out or something. Imagine the kind of catastrophe it can give us as a nation. So there are applications which require solution from Thermoelectrics, and we look forward. We can collaborate through our departmental this thing, and we have some very good organization which are working institutes which are working within Air Force, and we look forward to have some more interaction so that we can understand what exactly is being done at your end and what exactly we require. Once those things are synchronized, hopefully we can look forward and work towards betterment of this ecosystem, and as a nation we can go in the right direction. I've done, sir. Thank you. If you have any questions, you can.
I want to comment.
Yeah.
So first of all, Yogesh ji and Nimna ma'am, both of them, they are here. We are thankful to your headquarters for deputing you, both of you, and thankful to you also, both of you, to come here and involved in the proceedings like what was expected from the participants from an academic institution. आप अभी जो सारी बातें कह रहे थे, निश्चित रूप से देयर इज ए बिग गैप इन इंडियन एकेडमिया व्हाट इज बीइंग डन टेंजिबल आइटम तक आने तक। मुखिया सर यहाँ पर हैं जो कि CSIR NPL की जो लैब है सेमीकंडक्टर्स की उसमें पायनियर लैब है, पर क्या हम कितना एक टेंजिबल कोई इक्विपमेंट बना पाए जो सोसाइटी के लिए काम में आ रहा है, तो बहुत लिमिटेड चीज़ें हमारे अंगुलियों पर होगी कि ये बना पाए। सर भी हैं, कोई मुक्ता सर भी हैं, मैम भी है। तो निश्चित रूप से जो यंग जनरेशन सामने बैठी है उनको, और निश्चित रूप से जो एकेडमिशियंस आप लोग हैं, हमें एक नया ओरिएंटेशन लेना पड़ेगा कि हम सोसाइटी के साथ साथ जो बाकी सारी चीज़ें हमारे लिए इम्पॉर्टेंट है, अभी हम जो रिसर्च कर रहे हैं वो उसमें ज़्यादातर रिसर्च बहुत सॉफिस्टिकेटेड इंस्ट्रूमेंटेशन के लिए या वो इस तरह की चीज़ें जो कि बहुत इलीट लोगों के काम में आने वाली, पर निश्चित रूप से जो डिफेंस सेक्टर है वो हमारा बहुत बड़ा इट इज़ मतलब इंडियन सोसाइटी का एक बहुत बड़ा पार्ट, इंडिया की इकोनॉमी का एक बहुत बड़ा पार्ट वहाँ पर इन्वॉल्व है। और सबसे बड़ी बात, हमारी सेफ्टी के लिए लोग जो जान हथेली पर लिए घूम रहे हैं, निश्चित रूप से क्या हम इंडियन एकेडमिया में उनके लिए भी एक थॉट प्रोसेस रखते हैं क्या? तो वो यंग जनरेशन के साथ ये है कि एक नया थॉट प्रोसेस ले, चीज़ें इस तरह की। और निश्चित रूप से जैसे चेयरमैन साहब ने इनॉग्रल में कहा, जब आदमी सोचना शुरू करता है तो रास्ते निकल जाते हैं। तो निश्चित रूप से जो मटेरियल साइंटिस्ट और थर्मोइलेक्ट्रिक्स के फील्ड में लोग हमारे काम कर रहे हैं, हम लोग उस पर इस डायरेक्शन में ध्यान देंगे। और जैसा मैंने योगेश सर को कहा है कि निश्चित रूप से हम एक दो कोई प्रपोजल हमारे यहाँ से, तो बाकी सब लोग भी यू आर ऑल ओपन टू योगेश जी के नंबर लें। और निश्चित रूप से आप अगर करेंगे तो मैंने इनके हेडक्वार्टर को एक मेल भेजा था, पता नहीं इन तक कैसे पहुंचा है और क्या कम्युनिकेशन हुआ है, पर मेरे पास तो निश्चित रूप से व्हाट दे आर, अभी योगी जी ने कहा कि दे आर वेटिंग सच काइंड प्रपोजल्स, तो निश्चित रूप से इस तरह के प्रपोजल उधर जाने चाहिए और वी शुड बी एबल टू कंट्रीब्यूट। दिस विल बी द मेजर एंड द मोस्ट नीडेड कंट्रीब्यूशन फ्रॉम द इंडियन एकेडमिया। और विद दिस आई थैंक योगेश जी, उन्होंने काफ़ी मतलब यहाँ आने का जो पर्पज़ था वो इन्होंने बहुत स्पष्ट रूप से हमारे सामने रखा। और जो इंट्रिकेसीज हैं, जो डेटा में रिडंडेंसी के कारण जो भी प्रॉब्लम्स खड़ी हो जाती है इनके सामने, जब हवा में है कि गाड़ी साइड में लगा लो, एक बहुत बड़ा स्टेटमेंट है। वहाँ इतना एक फ्रैक्शन ऑफ ए सेकंड नहीं है, उसके बाद तो सब कुछ खत्म। इफ यू आर गॉन तो गॉन, बस उसके बाद तो कुछ सोचने को रहता ही नहीं है। तो निश्चित रूप से हम उन परिस्थितियों से इंट्रोड्यूस हुए हैं, ये एक बड़ी बात है। थैंक यू वेरी मच।
Basically, we have all these sophisticated equipment, but there are at times there are things which go unsolicited, and we at times are helpless because we don't have the required vendor support. Because in a place like Silchar, you don't have sufficient vendors who can provide these kind of items. Something as simple as batteries and all. These are the times when we want, like, young budding minds like you to understand our problems and come out with solutions. And right now I am posted to a place called 9BRE, and one of our main requirements is most of these equipments are to be used in aircraft. So it has to go through environmental testing. So you have to take into consideration that factors also, like what he said, that the difference in temperature, the vibrations. So when making something, you have to understand. So if you're making something, you must approach us so that we also, you should be clear with our requirement as to what we require, because we have to take into consideration many things. So it would be really helpful if you all contribute and help us with making something good.
Any more questions from any other student? Thank you. Thank you.
Now it is over, and let us thank all the speakers who has contributed in this session, and let us thank all the speakers once again, and I may hand over this to Professor.
Thank you everyone. I request Chair Dr. Chandana Rath to present memento to Dr. Raj Kishore Das from University of Hyderabad. And a memento to Dr. Vasundhara Mutta. Also, I request ma'am to present the memento, member mug, plant sapling and a folder to Dr. Ravindra Mukhia, CV Pilani. And to Dr. Govind Gupta, NPL. I also request Dr. Y.C. Sharma to present memento, member mug, plant sapling and a folder to Chair Dr. Chandana Rath. And a memento to co-chair Dr. Rekha Verma. Also to present a memento, member mug and plant sapling to Wing Commander Mr. Yogesh Betolia.
इनको कल दे देंगे फोटो तो खिंचवा
And a member mug and plant sapling to Wing Commander Limna Narayanan.
आप तो सब उधर जाओ है ना So thank you everyone. So we will be moving to the next session. That is the session number 7, poster session. So there are 9 posters which will be, 2 posters are online and others are in physical mode. Although we try to request the participants to present these posters also as e-posters, but they are insisting on physical mode. But we will begin best two posters, one poster will be awarded rupees 1100 from MRSA Rajasthan chapter. 1100. One. So best oral presentation will be awarded 2100 and poster will be 1100. So वो online है क्या तेरा? So now we request the session chair and co-chair, Dr. Ravindra Mukhya. He has gone, and Dr. Govind Gupta. Please, sir, you come in and take over the charge.
इसमें देखना अपने वाले लैपटॉप में
So these two online and बाकी सब Sanjukta, do you hear me? Sanjukta? Sanjukta? Yes, yes, audible. You have 5 minutes. Please share your screen and explain. We all are listening here. Yes, sir. Please start. Just share your screen. शेयर करें तो डिफिकल्टी है क्या जस्ट इस एरो पे आप एरो की पे जो इन्फ्लुएंस इस प्रेजेंट एरो पे क्लिक कीजिएगा ये जो नीचे है आप एरो की पे लाइक दिस वन और इट विल प्रेजेंट योर एंटायर स्क्रीन अभी आप देखिएगा ना ये इस पे आप क्लिक करेंगे ना आप इस पे जो अप एरो नीचे 6 बटन बन रहे हैं ना नीचे उसमें अप एरो की पे प्रेजेंटेशन पे वाले पे क्लिक करेंगे आपको स्क्रीन शेयर करना है जस्ट अब yes we are able to see now go on please Yes, just slightly enlarge it so that rest of the audience can see it. इसको बेटा मैक्सिमाइज कर सकते हो आपको मालूम ऊपर जो ब्लॉक होते दो रेक्टेंगुलर वन साइड होते ना उसको हाँ तो ओके बोलिए प्लीज स्टार्ट कीजिएगा 5 मिनट्स है आपके पास
or can generate clean energy. In this sense, the thermoelectric devices, the thermoelectric materials come into application which can convert the waste heat that is generated from various sources. For example, the automobile industry, the incinerators, thermal power plants, nuclear power plant, etc. And they can convert the waste heat into electricity. Now these devices are scalable, they are solid state devices and they have no moving part. The efficiency of this device depends upon the figure of merit, that is the ZP, which depend upon three parameters, that is the Seebeck coefficient, the electrical conductivity and the thermal conductivity. For higher figure of merit, we need a higher Seebeck coefficient, higher electrical conductivity and lower thermal conductivity. But the problem is that the Seebeck coefficient and the electrical conductivity, both of them are inversely related to the carrier concentration. With the increase in the carrier concentration, as we can see from the Visual plot, the Seebeck coefficient is decreasing, but the electrical conductivity is increasing. Thus, we need an optimum carrier concentration in order to have a high figure of merit. These parameters, that is the Seebeck as well as the electrical conductivity, are coupled with each other, and thus, in order to have a better thermoelectric property, engineering decoupling is required. And for this, we need a phonon glass electron crystal model, that in which we need a glass-like thermal conductivity and crystal-like electrical conductivity. I have worked on focused mainly on the thermoelectric material, that is a new class of material, TMPCs, which is the transition metal perovskite chalcogenide, which have a ABX3 perovskite structure and they have a wide tunable composition and structure. Moreover, the best part is they are made up of abundant materials. But now in this TMPC, for example, my structure, that is the barium titanium sulfide, I have replaced the oxygen with the sulfur. Now why I have done that? Because in case of oxygen, AbO3 type compound, because of the high electronegativity difference, it has an ionic character which tend to increase the band gap of this material. But when we replace this oxygen with the sulfur, the electronegativity difference decreases and the covalent character comes in, which leads to better charge transport and the band gap decreases widely. Now, I have synthesized the barium titanium sulfide with the help of the solid state route in sealed ampoules, and then I have densified the material with the help of the spark plasma sintering. With the help of this, the dense pellet, more than 95% density is observed, and then the pellet is used for various characterization, the structural characterization and the electrical characterization and thermal characterization, like the thermal diffusivity, specific heat measurement, power factor, Hall measurement, etc. When we talk about the structural and the optical characterization, we have seen, with the help of the XRD information, we have seen that the barium titanium sulfide exhibits a hexagonal structure. It crystallizes in a hexagonal structure. And then when I have done the UV visible spectroscopy of the material, I have seen that the band gap has drastically reduced to 2.06 electron volt as compared to 3.14 electron volt in the barium titanium oxide. Then the SEM studies shows that the elemental distribution is homogeneous in the microstructure and no extra secondary phases have been found. When we talk about the electrical properties of this material, with the help of the ZEM3, we have the conductivity, Seebeck coefficient, and power factor. Now the conductivity is increasing with the increasing temperature, but it is not much. But the most important part is the Seebeck coefficient. A high Seebeck coefficient is observed in this material, which make it a potential candidate for thermoelectric application. And one of the major significance is ultra low lattice thermal conductivity, as can be seen from this graph, that zero point 0.4 up to 0.4 we can get the thermal conductivity in these material, which is lowest than the commercial available tellurides in the ceramics, which are used in the thermoelectric industries. Now, from the DFT and computational calculations, we have found that the balance of the conduction bond, what are the orbitals that have been participating. The valence band is mainly composed of the sulfur p orbital, while the titanium is mainly composed of titanium d orbital. But in case of the barium, it is not contributing anything to the valence in the conduction band and lying as a weak bonding element, both the valence and the conduction band. Now, for the conclusion, I would like to conclude that these are very low classroom material. Moreover, most of these candidates show structural polymorphism, means they crystallizes in a wide variety of structures. There are not much studies, though not a lot of computational studies have been done on it, but experimental validation is still required. For thermoelectric application, because of the high Seebeck coefficient and ultra-low lattice thermal conductivity, they can stand up as a potential candidate for the thermoelectric application. From the oxide counterparts, as we have seen, the band gap has drastically reduced because of the sulfur substitution in place of oxygen. Most of these structures, for example, cerium titanium sulfide, show quasi one-dimensional structure having PISX chains and lying in a 1D, leading to a better charge transport. Moreover, the strong inharmonicity due to the soft covalent bonds between the metal and the chalcogen in these materials lead to ultra-low lattice thermal conductivity. At the end, I would like to thank the SERM as well as the IIT Kanpur for all the facilities that they have provided me. And also, I would like to thank the Japan National University for providing me an opportunity to present my work here. Thank you.
Sanjukta, what is the ZT of your material?
Hello, sir.
What is the ZT of your material?
ZT is actually 0.04 for this material that I have calculated.
Okay, what you can do to improve the ZT value in your material?
So please pardon.
What technique you have to adopt to increase the ZT of your material?
In order to increase the ZT of the material, one of the techniques that we can do is making a composite, or we can dope it with the suitable dopants to increase mainly the electrical conductivity, as you can see, is low. So if we had dope it with some constituent which can increase the electrical conductivity answer, so we can have a better ZT value.
What is the maximum you are expecting?
Maximum that I expect is like 0.4 or 0.5.
And what is the best ZT material available?
Yes, sir.
What is the best ZT material available?
So the SNSE, the tin selenide, that is has a very high ZT value. The polycrystalline form has a reported ZT value of 2. Or lead telluride have a very high ZT value of around 2.
So where do you see the application of your material from commercial point of view?
Actually, sir, my application is mainly. I think they don't means they won't be like that perfect, but yeah, with I don't know, with suitable doping or composites, they can increase up to 1 or something. Means by computational studies, they have shown that up to 1 they have reached, but I don't know experimentally whether it is validated or not. So experimental validation is required.
Okay. Any question from audience side? Okay, in that case, thank you, Sanjukta.
Thank you, sir. Thank you.
आपके साथ बस 5 मिनट में एक और ये लेना सर 6 हाँ एक ही है आपको किस हाँ हाँ पोस्टर देखिए फिर निकलिए नहीं एक और पोस्टर लिए तो है
अब तो ऑनलाइन है नहीं
अब नहीं है तो वहीं चलते हैं आइए
चलिए प्लीज पोस्टर प्रेजेंटेशन के लिए
और मैं आपको
आप बैठे हो ना
Thank you.